All right, let's take a look at the practice tests where the instructions were asked to describe the transformation from f of x to g of x and then sketch the graph of g of x. All right, for the first problem, we're given f of x equals x cubed and then g of x equals 1/2 times the quantity x minus 2 cubed and then minus 1. So for this one, I've already written it on the other page. So I think we know how to do this at this point. So this 1/2 right here, that's multiplying this guy, that's going to give me a vertical compression by a factor of 2. So I have here vertically compressed by a factor of 2. Again, I know a lot of you are going to say it's a vertical shrink by a factor of 1/2. Different terminology, same meaning. Then when we come on the inside right here, remember, when you have a transformation that involves x, you have to undo what's being done to x. So this is x minus 2. So I need to do plus 2 to undo that. So that means I'm going to be shifted 2 units to the right. Now when we come back on the outside, you have this minus 1. So we're going to go ahead and say that's going to shift me down by 1 unit. So just have shifted 1 unit down. So again, this order here could be changed because the transformations that involve x and y do not impact each other. So you could take this one right here where we say shifted 2 units right, and you could put it at the top, you could put it at the bottom. As long as you do this one, the vertically compressed by a factor of 2, before you do this one, shifted 1 unit down, you'll be okay. All right, so let's just say that on f of x, we have some x comma y. Then when we go to g of x, so g of x, this is going to go to, well, in terms of my x, I'm just shifting 2 units to the right, so it's just going to be x plus 2. So x plus 2. And then in terms of y, I'm going to multiply by 1/2, or again, you could divide it by 2. And then once that's done, I'm going to subtract away 1. So let's say this is y over 2, and then minus 1. All right, let me grab this. And let me come down here and paste this in. So we know what f of x equals x cubed looks like. Again, we've seen this a million times. This is the guy in red. So you have the point 0, 0, you have the point 2, 8, and you have the point -2, -8. So I'm just going to use those points to come over here. So again, if you have something like, let's say 2, 8, that is going to go to 2 plus 2 is going to be 4. And then your 8 would be divided by 2. That's 4. 4 minus 1 is 3. So 2, 8 is going to go to 4, 3. And then something like 0, 0, that's going to go to, well, 0 plus 2 is 2. And then 0 over 2 would be 0. And then minus 1 would be -1. So 0, 0 is going to go to 2, -1. And then the last point we'll do, we have this -2, -8. So that's going to go to -2 plus 2 is 0. And then -8 divided by 2 is -4. -4 minus 1 is -5. So this -2, -8 is going to go to 0, -5. So again, you know the general shape of this guy. Once you have these 3 points, that is enough to sketch the graph. It does not have to be perfect. You're just trying to get a general idea of what it looks like. All right, for problem 2, we have f of x equals x to the 4th power, and then g of x equals 1/4 times the quantity x plus 3 to the 4th power plus 1. So once again, I went ahead and just wrote this out already. We know that when we look at this g of x here, this 1/4 out in front, if you're multiplying by a 4th, you can say that you're vertically compressed by a factor of 4, or again, a vertical shrink by a factor of a 4th, whichever one you want to choose there. And then once we go on the inside right here, again, we have to undo what's being done to x. If you have x plus 3, well, to undo that plus 3, you need to subtract away 3. So that means I'm going to be shifted 3 units left. Then when we come back on the outside here, you have the plus 1. Again, that's shifting me up 1 unit. So I have shifted 1 unit up. Again, this one right here that I've listed as number 2, that can go first, that can go last. As long as you do the vertical ones in that specific order, in other words, vertically compressed by a factor of 4 first, and then shifted 1 unit up second, you'll be okay. All right, so I'm just going to say that for f of x, we have x comma y, and then for g of x, we have, again, for the x, I'm shifting 3 units left, so that's x minus 3. So x minus 3. For the y, I'm going to divide by 4, or again, multiply by a 4th, so y over 4. And then when I'm done with that, I'm going to add 1. Let me fix this. So let me just draw an arrow like that, and let's just go ahead and come down here and we'll look at the graph. So we've seen f of x equals x to the 4th power before. It's going to be this guy right here in red. It's a very skinny graph. So we can see that it looks similar to the graph of f of x equals x squared, but it's flatter around the origin and then steeper everywhere else. So something we talked about in the lesson. So a common point here would be 0, 0. Another one would be 2, 16. And then another one would be -2, 16. So you could just use those points. So let's say we start with 2, 16. What's that going to go to? Again, here we're taking the x value of 2, we're subtracting away 3, so that's negative 1. And then for the y value, it's 16. 16 over 4 would be 4. 4 plus 1 would be 5. So this 2 comma 16 is going to go to this negative 1 comma 5. Then if we look at something like, let's say 0 comma 0, that's going to go to, well, 0 minus 3 is negative 3. And then 0 over 4 is still 0, plus 1 is 1. So this 0 comma 0 is going to go to this negative 3 comma 1. So the last point we'll do is negative 2 comma 16. So negative 2 minus 3, that's negative 5. And then 16 over 4 is, again, 4. 4 plus 1 is 5. So this right here, this negative 2 comma 16, that's going to go to this negative 5 comma 5. Now I have some other points that I went ahead and put in. So you'll see that I have this 1 comma 1, and that's going to end up going to negative 2 comma 5 fourths. And then I also have this negative 1 comma 1, and that's going to go to negative 4 comma 5 fourths. So you can put those in if you need to. But I think the 3 points that we did would be enough to get a general shape of the graph. Again, this does not have to be perfect. All right, now we're going to change up the instructions. We want to describe the end behavior of each polynomial function. All right, for problem 3, we're given f of x equals negative 2x to the 6th power plus 4x cubed minus x squared plus 1. So again, we want to use the leading coefficient test. So we first start with the leading term. So it's going to be this guy right here. So negative 2x to the 6th power. And then the leading coefficient is just the negative 2. So of course that's negative. And the degree is 6, which is an even number. So that tells me that this is going to match, again, just think about the upside down parabola. If you had something like f of x equals negative x squared. So the graph falls to the left and falls to the right. Again, you can always graph this on Desmos or something like that for confirmation. This is your f of x equals negative 2x to the 6th power plus 4x cubed minus x squared plus 1. So again, the graph falls to the left and falls to the right. All right, for problem 4, we have f of x equals 5x cubed minus x plus 3. So now the leading term is going to be 5x cubed, so this guy right here. The leading coefficient is 5, which is positive, and the degree is 3, which is odd. For this one, you can think about f of x equals x cubed or f of x equals x. So the graph falls to the left and rises to the right. So again, just graphing this for confirmation, this is f of x equals 5x cubed minus x plus 3. So again, the graph falls to the left and rises to the right. All right, let's change up the instructions. So we want to identify the x-intercepts and describe the shape of the graph near that x-intercept. All right, let's take a look at problem 5. So we have f of x equals 1/10 times the quantity x minus 1 cubed times the quantity 2x minus 5 squared times the quantity x plus 1. Now, you see that I've done some factoring here. I'm going to explain this in a moment. Remember, there's different ways you could get your zeros and come up with your x-intercepts. So one way you can do this, probably the most common approach, is just to take this guy right here, set it equal to 0, and then solve using the zero product property. So let's just do that first. So we would have something like 1/10 times the quantity x minus 1 cubed times the quantity 2x minus 5 squared, and then times your quantity x plus 1, we're going to set this equal to 0. So the first thing I would do here is just multiply both sides by 10. So multiply by 10 over here, multiply by 10 over here. So we know that 0 times anything is 0. So let me put 0 there. And then over here, 10 times 1/10, that's just going to be 1. So basically you would have the quantity x minus 1 cubed times the quantity 2x minus 5 squared times the quantity x plus 1. So this is set equal to 0. So again, you can just use your zero product property. You're going to take each factor and set it equal to 0 and solve. So something like x minus 1 cubed, if you set that equal to 0, you could just solve x minus 1 is equal to 0. And we're going to add 1 to both sides. This cancels. You get x is equal to 1. So what this tells me is that, let me just put this here, you would have an x-intercept at 1, 0. Now this 3 here, the exponent is important because that's giving you the multiplicity of that 0. So 1 is a 0 with multiplicity 3. We'll talk more about that in a moment. Let me just continue here. So I'm going to go or. So now you'd have the quantity 2x minus 5 squared is equal to 0. And again, you could just solve 2x minus 5 is equal to 0. We would add 5 to both sides of the equation. This would cancel. You get 2x is equal to 5. Divide both sides by 2. This would cancel. So you're going to get x is equal to 5 halves. So x is equal to 5 halves. So 5 halves would be a 0 there, and the multiplicity would be 2. So that would lead to an x-intercept, which is 5 halves, 0. Then the last one, we would say x plus 1 is equal to 0. Just subtract 1 away from each side. So you get x is equal to -1. Let me put that like that. And so this one, the 0 would be -1. The multiplicity there, again, because this exponent is understood to be a 1, would just be 1. So here this would be -1, 0. Another way you could do this is by factoring. So sometimes the teacher will ask you to put everything in the form of x minus k, so you can just grab the zeros. So this one, what you'll look at here is you don't want to pull the 2 straight out and bring it out here because this is squared. That's a common mistake when people are factoring. What you'd want to do is first pull the 2 out inside of these parentheses. So in other words, here you would write this first as f of x equals 1/10 times the quantity x minus 1 cubed. And then this right here would be the quantity 2 times the quantity x minus 5 halves. And then this whole thing would be squared. So doing it this way, you haven't done anything illegal. So you could multiply 2 times x, that's still 2x. And then minus and minus, 2 times 5 halves would be 5. So this whole quantity is squared, just like this one. Then you have this quantity x minus -1, again, just changing the x plus 1 over to x minus -1. So this one can actually be simplified a little bit. What you can do is use the rules of exponents. Remember, this is multiplication here. So let me put a little border. If you have something like a times b, and this is squared, this is equal to a squared times b squared. So we're just going to use that rule here. So we'll say that we have 1/10 times the quantity x minus 1 cubed. And then this, again, you could just say times 2 squared, and then times this quantity x minus 5 halves squared. So hopefully that makes sense. I'm just using the rules of exponents. Since this is multiplication right here, this exponent of 2 would be applied to the 2. That's one of the factors. And then it would be applied to this x minus 5 halves. That's the other factor. Again, that quantity. Let me fix this right quick. And then we would have times this quantity x minus a -1. So we would have 2 squared, which is 4. So you'd end up with 4/10 here. And 4/10 is nothing more than just 2/5. And then this is times the quantity x minus 1 cubed. And then times the quantity x minus 5 halves squared. And then times the quantity x minus a -1. All right, so I went ahead and wrote this more cleanly. So here's the f of x equals 2/5 times the quantity x minus 1 cubed times the quantity x minus 5 halves squared times the quantity x minus a -1. So in this form here, you could just grab the zeros. So you have 1 of 1 with a multiplicity of 3. Again, that's coming from that exponent right there. You have 1 of 5 halves with a multiplicity of 2. Again, that's coming from that exponent right there. And then you have 1 of -1 with a multiplicity of 1. Again, because this right here, let me just put it in, is understood to be 1. So the x-intercepts, again, you can have 1, 0. That's coming from this right here. And the multiplicity is 3, which is odd. So we're going to cross through the x-axis. Then you have your 5 halves, 0. So again, the multiplicity of that 0, 5 halves is 2. That's even. So we're going to touch the x-axis and turn around. And then you have -1, 0. So for that one, the multiplicity for that 0 of -1 is 1. So that's odd. So we're going to cross through the x-axis there. Now, it did not ask for it, but just keep in mind that when you have a 0 and the multiplicity is 1, it's just going to cross straight through. And when the multiplicity is greater than 1, it's going to flatten out near that 0. So just keep that in mind if you're trying to use this to sketch something. So here's the graph so we can confirm things. So we have f of x equals 1/10 times the quantity x minus 1 cubed times the quantity 2x minus 5 squared times the quantity x plus 1. If you want to type in the factored form that I just gave you into Desmos, you'll get the same graph. So you'll see at -1, 0, again, we cross straight through, right? Because the multiplicity of that 0 was 1. Then if you look at 1, 0, again, we're going to cross through, but we're going to flatten out when we do that. Then when we look at 5 halves, 0, we're going to touch and turn around. Okay, so touch and turn around. Again, odd multiplicity, even multiplicity. So we talked about why we have that behavior in the lesson. So just remember that if you're trying to use this to sketch the graph. All right, let's take a look at problem 6. So for this one, we're given f of x equals 1/3 times the quantity x minus 2 cubed times the quantity x minus 5 squared times the quantity 2x minus 9. Now, in this particular case, again, you could take this right here, so this right here, and just set it equal to 0 and solve. So that would be one way to get the zeros. But I just prefer to factor it because it's nice and clean, and you can quickly see what the zeros are going to be. In this case, it's a lot easier because you have a coefficient on x here of 1, and then a coefficient on x here of 1, so you don't have to really worry about that. Here, the coefficient on x is 2, so you could pull it out. But in this case, the exponent here is a 1, so you don't have to worry about doing what we did in the previous problem. So you could just pull the 2 out, so it comes out in front. So 2 times a third is 2/3, so that's where that's coming from. And then inside, you just divide everything by 2. So 2x divided by 2 is going to be x, and then -9 divided by 2 is -9 halves. So now that you have this in factored form, again, you can very easily get these zeros. So f of x equals 2/3 times the quantity x minus 2 cubed times the quantity x minus 5 squared times the quantity x minus 9 halves. So you have a 0 of 2, and again, the multiplicity would be 3 coming from that exponent. You have a 0 of 5, the multiplicity would be 2, again, coming from that exponent. And then you have a 0 of 9 halves, and the multiplicity would be 1. Again, you could put an exponent of 1 there for clarity. So in terms of what's going to happen at your x-intercepts, So at 2, 0, you're going to cross through the x-axis. That's because this guy right here, this 0 of 2, has an odd multiplicity. The multiplicity is 3. Then at 5, 0, we're going to touch the x-axis and turn around. Well, if we look at this one again, this is 5 for the 0. The multiplicity is 2. That's an even multiplicity, so that's why that's happening. Then at 9 halves, 0, we're going to cross through the x-axis. And that's because when we come up here, this 0 of 9 halves, the multiplicity is 1. That's odd. So here's our graph. And again, this is one you might want to use Desmos for. I gave you a link, so just scroll in because 9 halves, 0 and 5, 0, those are very close together on this graph. But you'll notice that at 2, 0, again, the multiplicity of this 0 was 3, so it's odd, so it's going to cross through, and it's going to flatten out a little bit. Then what's going to happen is at 9 halves, 0, again, 9 halves had a multiplicity of 1. We're going to cross straight through, so it's not going to flatten out there, but it is going to have to turn around immediately because these guys are so close together. And then at 5, 0, again, we had an even multiplicity for that 0 of 5. This guy's going to come back, it's going to touch and turn around. All right, so the instructions are going to change. We want to use the given function to state the maximum number of turning points and use the given graph to identify the local maximum and minimum points. All right, for problem 7, we have f of x equals 1/4 x to the 4th power minus 2x cubed plus 11 halves x squared minus 6x plus 17/4. Again, for the maximum number of turning points, not necessarily the number of turning points, but the maximum number of turning points, you want to look at the degree of your polynomial function. So in this case, the degree is going to be 4. And all you want to do is subtract away 1 from that. So 4 minus 1 would be 3. So the maximum number, let me highlight that, the maximum number of turning points is 3. Remember, you could have less than that. This is just the maximum number. Okay, so let's go to the graph now. And we're looking for the local minimum points and the local maximum points. So when I say a local minimum point, what am I talking about? I'm talking about a point where we're changing from decreasing to increasing. So it's going to form a valley. In other words, if I draw my walking guy, so he's walking. Right now we're decreasing, decreasing, decreasing. And then when we get to this point 1, 2, we're going to change over. So now this guy is going to be increasing. So 1, 2 would be a local minimum point. And then the same thing would be for this point right here, which is 3, 2. We're changing from decreasing to increasing. So this 3, 2 would also be a local minimum point. So coming down here, I have local minimum points. So 1, 2, and then 3, 2. Now in terms of a local maximum point, that's where you're changing from increasing to decreasing. So this guy right here, he's walking up, right? So we're increasing. And then when we get to this 2, 9/4, he's going to change over to decreasing. So it forms a hill. And so basically this would be a local maximum point. So we're going to have a local maximum point at 2, 9/4. All right, let's take a look at problem 8. So here we have f of x equals negative x cubed plus 6x squared minus 9x plus 4. So for this one, the maximum number of turning points, again, you just look at the degree, which is going to be 3. You subtract away 1, that's going to be 2. So the maximum number of turning points is 2. Again, it doesn't have to be the number of turning points. It's just the, let me highlight this, the maximum number. So very important to understand that. Now, when we look at the graph, we're looking for the local minimum points and the local maximum points. So again, for a local minimum point, it's where you're changing over from decreasing to increasing. So I'm decreasing, decreasing, decreasing. I get to this point 1, 0, and I'm going to change things over. Now I'm going to be increasing. So this guy right here, this 1, 0, is a local minimum point. Notice that it forms a little valley. Then we're coming up here and we're forming a little hill. So 3, 4 is going to be a local maximum point. That's where you're changing from increasing. Again, this guy's walking up to decreasing. So increasing, increasing, increasing. You get to 3, 4, then you're going to change over to decreasing, decreasing, decreasing. So that would be our answer here. So 1, 0, that would be your local minimum point, and 3, 4 would be your local maximum point. I went ahead and wrote that out. So local minimum point, that's going to occur at 1, 0, and then the local maximum point here is going to occur at 3, 4. All right, let's change up the instructions now. So we want to create a rough sketch of each function. And for problem 9, we have f of x equals 2 times the quantity x minus 1 times the quantity x minus 5 times the quantity x minus 3. If you simplify this, you would get f of x equals 2x cubed minus 18x squared plus 46x minus 30. So if you want to sketch the graph of this guy, again, the first thing you would think about is the end behavior. So you have this 2x cubed as the leading term. And so I have all this written out so I can just go through it quickly. We said the leading term is 2x cubed. The leading coefficient is positive 2. And the degree of the leading term is 3, which is odd. The end behavior for the graph will be that it falls to the left and rises to the right. Again, for this one, you could just think about, well, what happens for f of x equals x cubed? Or what happens to f of x equals x? Something like that. Then I have the x-intercepts. Let me go back up. and show you where that's coming from. In factored form, this is written where it's x minus k. So x minus 1 here, you have x minus 5 here, and then x minus 3 here. So you have a 0 of 1, 5, and 3. Each has a multiplicity of 1, and so you get an x-intercept of 1, 0, 5, 0, and 3, 0. So coming back down, I have the x-intercepts are 1, 0, 3, 0, and 5, 0. The multiplicity is 1 for each 0 here, so the graph will cross through the x-axis at each x-intercept. And again, because the multiplicity is 1, it's just going to cross straight through. It's not going to flatten out. Now, the next thing is the y-intercept. So if you plug in a 0 for x there, you would have f of 0. All this would go away. You just say this is equal to negative 30. Now, when I graph this guy, I'm not going to put the y-intercept on there, and that's just because of the scale of things. If you want to change your graph to fit this on there, that's fine. It's not that big of a deal. Again, you can always use Desmos to check things, and you could scroll in or out just to see your 0, negative 30, which is the y-intercept. So the y-intercept occurs at 0, negative 30. I have here this function is not odd or even, so we won't use origin symmetry or y-axis symmetry. Again, we know those tests for even and odd functions, so you can do those on your own if you want. I'm just going to tell you in advance it's not an even function and it's not an odd function. All right, coming down, I'm just going to put what I have so far. So it falls to the left and rises to the right. And then we have an x-intercept at 1, 0, 3, 0, and 5, 0. And keep in mind this guy is crossing straight through each time. So crossing straight through, crossing straight through, crossing straight through. The next thing I would recommend you do is get some points. So you make some intervals. So one interval is anything less than 1. Another one is between 1 and 3. Another one is going to be between 3 and 5. And then a final one would be anything greater than 5. You could just pick anything you want in each interval. So I'm just going to pick an x value of 0.75, and I'm going to get a y value that's negative 4.78. Now this is going to be an approximation for the y value, so just keep that in mind. So that point would be right here. So let's say 0.75 comma negative 4.78. Then if I go to the next interval, I can pick 2 for the x value. I get a y value of 6. That's going to be this right here, so 2 comma 6. In the next interval, I'm going to pick 4 for the x value. I'm going to get a y value of negative 6. So this is 4 comma negative 6. And then in the last interval here, I'm going to pick an x value of 5.25, and I'm going to get 4.78. Just keep in mind that the y value there is an approximation. So this is your 5.25 comma 4.78. The last question here is, where are the turning points? And this is the biggest problem when you're doing this without calculus. If you're in a calculus class, you can just take the derivative, set it equal to 0, and solve. But we don't know how to take a derivative yet, so we're left with this time-consuming approximation. If you don't want to do this, it's okay. Most teachers will just accept it. Otherwise, you could just plug in a lot of stuff here. You know that there will be a turn between 1 and 3 and between 3 and 5. So if we go back, how do I know that? Because the graph's going to do something like this. It's going to come up, it's going to turn, it's going to come back down, it's going to turn, it's going to come back up. So I know that I'm going to have somewhere between 1 and 3 and then somewhere between 3 and 5. I'm looking for my turns. So between 1 and 3, what I'm looking for is a local maximum point. So just look for the y value that's going to be the largest. That's going to be right here. So that's going to be at about 1.85 comma 6.16. So I'm going to say that there's a local maximum point. Again, this is an approximation. It's not going to be perfect. So let's say about 1.85 comma 6.16. So that would be one of your turns. Then looking at this guy right here, I'm looking for a local minimum point. So local minimum point. And for this one, I'm looking for the smallest y value. So that's going to be right here, negative 6.16. So let's say the turn here is going to be about 4.15 comma negative 6.16. So again, this is an approximation. So you just get it as best as you can. I put in a lot of work here, just a lot of plugging in and things like that. Again, you might not have time for that, or you might not want to do that. So if you want to skip it, it's fine. Or if you want to choose less values and have a less accurate turn, that is completely up to you. You're not expected to get a perfect turn until you get to calculus. And I'm going to go ahead and take everything that we've found so far and just sketch the graph. Of course, this is computer generated, so it's perfect, but yours is not going to be, and that's okay. So we have f of x equals 2x cubed minus 18x squared plus 46x minus 30. You see you have your point, which is 0.75 comma negative 4.78. That's right there. You have your 1 comma 0. You have your 2 comma 6. Again, you would have your turn here, which is about 1.85 comma 6.16. And then we come back down. So we have this 3 comma 0. We have 4 comma negative 6. Then you'd have your turn here, which again is about 4.15 comma negative 6.16. And then you come back up and you're going to come through 5 comma 0. And then you have your 5.25 comma 4.78. So with that information there, you can make a pretty accurate sketch. Again, it's not going to be perfect and it doesn't need to be. All right, let's take a look at problem 10. So here we have f of x equals the quantity 2x minus 3 squared times the quantity x minus 4 squared. If you factor this to where you have something of the form of x minus k, you're going to have f of x equals 4, and that's coming from the fact that this is squared, so be careful if you're factoring here, times the quantity x minus 3 halves squared times the quantity x minus 4 squared. And we could just scroll down to this one. We don't need the other one. This is if you simplify, so this would take a long time, but f of x equals 4x to the fourth power minus 44x cubed plus 169x squared minus 264x plus 144. We know the leading term is 4x to the fourth power. So I have here the leading term is 4x to the fourth power, the leading coefficient is positive 4, and the degree of the leading term is 4, which is even. So the end behavior for the graph will be that it rises to the left and rises to the right. Again, just think about f of x equals x squared. So coming back up, now we're going to think about the zeros. So you have 3 halves and you have 4. In each case, the multiplicity is 2. So you can have an x-intercept that's 3 halves comma 0 and an x-intercept that's 4 comma 0. And I have here the x-intercepts are 3 halves comma 0 and 4 comma 0. The multiplicity is 2 for each 0 here. So the graph will touch the x-axis at each x-intercept and turn around. That's because the multiplicity is even, right? So if it's 2 or 4 or 6, something like that, it's going to touch and turn around. I have here that the y-intercept occurs at 0, 144. So that's coming from, if you said f of 0, this equals, again, all of this is going to go away. You're just left with 144. I'm not going to put this on my graph. Again, you can change your scale and put it on yours if you want. That's up to you. Then we have the function is not odd or even, so we won't use origin symmetry or y-axis symmetry. Again, we know the tests for those. You can try those on your own if you want, but I'm going to tell you it's not odd or even, so we're just going to move along. Just thinking about what we know the graph is going to rise to the left and rise to the right. We know we have an x-intercept, which is at 3 halves or 1.5, comma 0, and we're going to have an x-intercept at 4, comma 0. And we know that, again, these are going to touch and turn around here. So far, this is what we know. Now, the next thing I would do is make a little table just to get some additional points. So again, we can split the number line up into intervals. So anything less than 1.5, anything between 1.5 and 4, and then anything greater than 4. So I went ahead and picked an x value of 1 in this interval here. And so the y value is 9, so this is 1, 9. Then I picked an x value of 2, and I got a y value of 4, so that's in this interval here. So this is 2, 4. I went ahead and did another point in that interval, so I picked an x value of 3, got a y value of 9, so this is 3, 9. And then I went ahead and picked an x value of 4.5 in this interval here, and I get a y value of 9. The next issue is going to be the turning point. So this is going to come down like this, and then come back up, and then it's going to come down, and then come back up. So you're going to have a local maximum you need to find. So I'm looking between 2 and 4 here, and I'm just looking for the highest y value that I get. So it looks like it's going to be right here. So something about 9.77, that is an approximation, and that occurs with an x value of 2.75. So I would say that there's a local maximum point. And let me fix this. So point at about 2.75, 9.77. So it turns out that if you use calculus, 2.75 is actually the x value for the local maximum point. The y value here is just approximated. So it's not exactly that, but it's pretty close. So coming down, you have enough information to sketch the graph. So we're going to come down like this, do that 0.1, 9, and then we're going to come down. We're going to hit that 1.5, 0, turn around, come through that 0.2, 4. We're going to come up. Again, the x value here is 2.75. The y value is going to be about 9.77. So then we would have our turn. We would come back down. So we would have our 3, 9, come down, come down, come down. We're going to hit that 4, 0, and come back up. And then we're going to go through that 4.5, 9. So again, your graph does not need to be perfect. Just get it as close as you can. All right, let's take a look at the practice tests. For the instructions, we're asked to give the asymptotes and intercepts and then sketch the graph. All right, for problem 1, we have f of x equals 2 over x plus 1 and then plus 1. So for this situation, I'm going to use graphing transformations. So I'm going to use g of x equals 1 over x as the parent function. And so I'm going to say that f of x is equal to, I'm going to write this in terms of g of x. So I have this 2 right here that's multiplying this guy. So let's go 2 times g of, we're going to have this right here, this x plus 1. That's going to get plugged in for that x. So this right here is going to get plugged in right there. So let's put x plus 1 right there on the inside. And then we're going to have this plus 1 out here. So we'll put this on the outside, so plus 1. So when we look at this guy, it makes it really easy to get a list of our graphing transformations. Remember that we can just go left to right. So we can just say that this is 1, and then this is 2, and then this is 3. The vertical transformations follow the order of operations. So you multiply first, you add second. The horizontal transformations follow the reverse of the order of operations. In this case, you just have 1, so that's really not going to come up. So what I'm going to do first is deal with this 2 that's multiplying this guy. So that gives me a vertical stretch by a factor of 2. Then I'm going to come on the inside. So you have this plus 1 right here. When we go on the inside, we need to undo what's being done to x. So you have x plus 1 there. To undo that, you want to subtract away 1. So you're going to get a shift that is going to be 1 unit left. So shift 1 unit left. Then when we come back on the outside, again, this is going to be for vertical. We have this plus 1. And so that's going to be a shift that is 1 unit up. So the main thing here to understand if you're using graphing transformations is you know your points for g of x equals 1 over x. So those should be memorized. We should know the graph. So if you have a point on g of x, which is x comma y, the corresponding point on f of x is going to be x minus 1. That's coming from the shift 1 unit left. And then comma, you have 2 times y, again, because we have a vertical stretch by a factor of 2, and then plus 1 because we're shifting 1 unit up. Now again, we multiply first and then we add second. We're following the order of operations when we deal with vertical transformations. That's why this is 2y plus 1. Okay, so looking at the left here, those are going to be the points that we know from our g of x equals 1 over x. So these are corresponding points. So negative 2 comma negative 0.5, that's going to go to negative 3 comma 0. I'm going to highlight that. That's going to be the x-intercept. Then we have negative 1 comma negative 1. That's going to go to negative 2 comma negative 1. Negative 0.5 comma negative 2. That's going to go to negative 1.5 comma negative 3. 0.5 comma 2. That's going to go to negative 0.5 comma 5. 1 comma 1 is going to go to 0 comma 3. That's going to be the y-intercept. So I'll highlight that. And then 2 comma 0.5 is going to go to 1 comma 2. So before we sketch the graph, remember we want to give the asymptotes and intercepts. So we already figured out the x-intercept was negative 3 comma 0 and the y-intercept was 0 comma 3. But what if we weren't lucky? In other words, what if we hadn't found it? What do we do? Remember that this guy right here, if you set that equal to 0 and you solve, you're going to get your x-intercept or x-intercepts. You might not have them, but in this case, you will have 1. So I'm going to make this easy on myself, and I'm going to rewrite this function by getting a common denominator. So I'm going to go 2 over x plus 1, and then plus for 1, I'm going to write x plus 1 over x plus 1. And then if we add these guys, you're going to get x plus 1 plus 2 over x plus 1. So this becomes x plus 1 plus 2 is 3 over x plus 1. So let me erase the middle steps here. And I'm just going to write that this is equal to x plus 3 over x plus 1. So it's a lot easier to deal with it in this form because if I want to set this equal to 0, in other words, if I want to say x plus 3 over x plus 1 is equal to 0, well, again, for a fraction to be equal to 0, the numerator needs to be 0 and the denominator needs to not be 0. So all I have to do is say x plus 3 equals 0. Subtract 3 away from each side of the equation. This would cancel, and you get x is equal to negative 3. So you see we have our x-intercept, which occurs at negative 3 comma 0. In terms of the y-intercept, all you have to do is find f of 0. So that one's really easy. So if you wanted f of 0, that would be equal to, well, you could do it in this form or this form. It doesn't matter. I think we'll just work with this. So we'll go 0 plus 3 over 0 plus 1. And of course, this is 3 over 1, which is 3. So that's going to occur at 0 comma 3. So let's say that, let me move this out of the way. You're thinking about this guy right here, and you say, what is the vertical asymptote and what is the horizontal asymptote? Well, this denominator here and this denominator here, they match. So you'd be okay to say x plus 1, set that equal to 0 and solve. Subtract 1 away from each side of the equation. You get x is equal to negative 1. So you're still going to get that. The quicker way to do that is when you're dealing with graphing transformations, let me move this back up here. You would say that, well, for g of x is equal to 1 over x, well, the vertical asymptote is going to occur at x equals 0. So when I think about what transformations were applied to this guy, we just had a shift that was 1 unit to the left. And so basically, you're going to take your x equals 0, and you say, well, 0 minus 1 would be negative 1. So based on that, the new vertical asymptote, if I look at my f of x, is going to be x is equal to negative 1. So this is going to be for f of x. When we think about the horizontal asymptote, you're going to follow the same strategy. So we know that the shift was going to be 1 unit up. So we would say here it was y equals 0. That's on the g of x equals 1 over x. Well, when we get to f of x, now it's going to be y is equal to positive 1 because there's a shift up by 1 unit. Remember, the transformations for y, you multiply by 2 first. Well, 0 times 2 is still 0. And then you add 1 Second, well, 0 plus 1 is 1. But the other way to do it would be to look at it in this form right here. You have to be really, really careful about what you're doing, because where people make a mistake is they look at this form right here and they say, okay, well, 2 over x plus 1, that tells me that this is going to be y equals 0, but then they don't think about this over here. You have this plus 1, it's shifted up by 1 unit. It's better to actually look at it in this form right here, because you have the same degree in the numerator as the denominator. So when that happens, you have the ratio of the leading coefficients. So it's 1 over 1, which is 1. So that's why you get y equals 1. That's going to be your horizontal asymptote. All right, coming down to the graph. So these are just the points that we've already found. So this is -1/2, 5, 0, 3, and then 1, 2. So you can see that the way we would draw this is going to approach your vertical asymptote, which is x equals -1. So like that. Comes down like this, and it's going to approach that horizontal asymptote, which is y equals 1. Then this one, we have your -3, 0, you have your -2, -1, and then your -3/2, -3. So again, this is going to approach your horizontal asymptote like that. It's going to come down here and approach that vertical asymptote like that. One thing you might want to show for your teacher is that it's never going to impact this horizontal asymptote, and that's pretty easy to do. You would basically just say that this guy right here would be 1. So is that going to be possible? So 1 is equal to 2 over x plus 1, and then plus 1. If you subtract 1 away from each side, you would be solving 2 over x plus 1 is equal to 0. So is that possible? And the answer is no. And why is it no? Remember that for a fraction to be 0, the numerator needs to be 0, and the denominator needs to not be 0. Well, the numerator here is 2, so that's never going to be 0. So that means that 2 over x plus 1 can never be equal to 0. And so this 2 over x plus 1 plus 1, that's never ever going to be equal to 1. So the graph would never impact the horizontal asymptote, y equals 1. All right, let's take a look at the second problem. So we have f of x equals -2x minus 2 over x plus 6. Now, at first glance, if you were to compare this to, let's say, g of x is equal to 1 over x, you might be thinking, how could we use graphing transformations for this? But I showed you an example in the lesson where, again, you could just do some polynomial long division or synthetic division in this case, and you can convert this over to something where you can use graphing transformations. So in this case, you want to write x plus 6 as x minus a -6, so it matches the form of x minus k. So you can have a -6 out here, and then you're just going to take -2 and put it here, and then -2 and put it here. So then we could just do our synthetic division. We drop this down. So you have this -2 right here. So -6 times -2, that's positive 12. And then -2 plus 12, that's 10. So this would be equal to, remember, you're going to drop this by 1 degree. So if this is to the first power, this right here would be the coefficient for x to the power of 0. In other words, this is going to be your constant. So we would say this is -2 plus 10 over, you're going to use this denominator here. So this x plus 6. So I went ahead and just rewrote this. So we have f of x equals 10 over x plus 6. And then we have -2. Again, comparing this to g of x equals 1 over x, you could say that f of x is equal to, well, you have this 10 here. That's multiplying the guy. So 10 times g of, we're going to look at this right here, this x plus 6. That's getting plugged in for x right there. So this right here is going right there. So this would be x plus 6. And then you have this -2 on the outside. So let's put -2 like that. So just coming down here, again, we have f of x equals 10 times g of x plus 6, and then -2. We're working left to right. So this 10 that's multiplying this guy, that's giving me a vertical stretch by a factor of 10. Then this plus 6 on the inside, remember, I have to undo things on the inside. So if I have x plus 6, I want to undo that by subtracting away 6. So that means I have a shift 6 units left. And then coming back on the outside, I have this -2, and that's going to give me a shift 2 units down. So a given point on your g of x equals 1 over x, some x comma y, when we think about the corresponding point on f of x, it's going to be x minus 6, comma, 10y minus 2. All right, so again, I've already pre-written these points just to save a little time. So -2 comma -0.5, that's going to go to -8 comma -7. Then -1 comma -1, that's going to go to -7 comma -12. -0.5 comma -2, that's going to go to -6.5 comma -22. 0.5 comma 2, that's going to go to -5.5 comma 18. 1 comma 1 is going to go to -5 comma 8. 2 comma 0.5, that's going to go to -4 comma 3. Then in terms of finding the intercepts and the asymptotes, remember that for the x-intercept, what you can do, you can just take this original form. You want to set this equal to 0 and solve. So if I said, let me put a little border here, -2x minus 2 over x plus 6 is equal to 0. Again, a fraction is equal to 0 if the numerator is 0 and the denominator is not 0. So I just take -2x minus 2 and set that equal to 0, and I would add 2 to both sides. So I get -2x is equal to 2, then divide both sides by -2, and you're going to get x is equal to -1. So that means the x-intercept is going to occur at -1 comma 0. So what about the y-intercept? So for this, you're going to look at f of 0. So this equals negative 2 times 0 minus 2 over 0 plus 6. So this right here would go away. You would basically have negative 2 over 6, which is going to simplify to negative 1/3. So the y-intercept, let me fix that, is going to occur at 0, negative 1/3. So coming down here, we have the x-intercept, which is negative 1, 0, and then the y-intercept, which is 0, negative 1/3. For the vertical asymptote and the horizontal asymptote, again, if you want, you can look at this guy in this form right here. That's fine. Or you can just use the shifts that we found earlier. That's faster. Again, when you think about g of x is equal to 1 over x, the vertical asymptote is going to occur at x is equal to 0. Well, we know that we had a shift that was 6 units to the left, so now the vertical asymptote is going to occur at x equals negative 6. The other way to do that is just take the denominator. So you could take x plus 6, set that equal to 0 and solve. Subtract 6 away from each side, you get x equals negative 6. So it's the same either way. Let me fix that. And then for the horizontal asymptote, again, you could look at this guy over this guy. You can see that this is a first degree and this is a first degree. So then when that happens, you want the ratio of the leading coefficients. So it would be negative 2 over 1. So you would get y equals negative 2. But the other way to do it is to think about, well, in this g of x equals 1 over x, you have a horizontal asymptote, which is going to occur at y equals 0. Now, what was the vertical shift for this guy? We were going down 2 units. Again, you can't really see that here. You have to use this form right here. Remember, we had to shift 2 units down. So coming back, that's why you see the horizontal asymptote, which is going to be y equals negative 2. All right, let's come down to our graph. So we have f of x equals 10 over x plus 6, and then minus 2. So just thinking about this, we have our points, so negative 11 over 2, 18. That's this right there. Negative 5, 8. This is negative 4, 3. Negative 1, 0. And then 0, negative 1/3. Over here, you have your negative 8, negative 7. Your negative 7, negative 12. And your negative 13 halves, negative 22. So the scale of this is a little bit different. Again, I gave you a link for everything on Desmos. So you can just click it if you need to zoom in. So this guy right here, again, we're drawing it to where it approaches this vertical asymptote, which is x equals negative 6. It's going to come down here like this. And then it's going to approach the horizontal asymptote, which is y equals negative 2. Same thing for this one. So this is going to approach this horizontal asymptote, which is y equals negative 2. And we're going to have this curve right here. And this is going to be drawn to where it approaches this x equals negative 6. And then once again, this is not going to impact this horizontal asymptote, this y equals negative 2. You could put negative 2 is equal to 10 over x plus 6 and then minus 2. Again, if you add 2 to both sides, you're going to get that 10 over x plus 6 is equal to 0. And as we talked about in the last problem, this is impossible because you would need the numerator to be 0 and the denominator to be non-zero, and 10 is never going to be 0. So this right here has no solution. So we're not going to impact that horizontal asymptote. All right, for problem 3, we have f of x equals 4 over the quantity 1/3 x minus 2 squared and then minus 5. All right, the first thing I'm going to do, since we're going to be using graphing transformations here, I'm going to factor out this 1/3 down here. That's going to make it a little bit easier to work with. So I'm going to have f of x equals 4 over. We're going to have some brackets here, and we're going to say 1/3 times the quantity, x minus 6. So this is all squared. And then we have minus 5. If you're having trouble with this factoring, remember that if you pull out a 1/3 from this, it's very obvious that this would be x. But then this part is where people struggle. Just think about how can I undo multiplication by a third? Well, I would multiply by 3. So negative 2 times 3 would be negative 6. And if you check this, 1/3 times x is 1/3 x, and then minus and minus, 1/3 times 6 is going to be 2. So this would be a match. Now, if we compare this to our g of x equals 1 over x squared, what are we going to have? Well, let's write our f of x in terms of g of x to see that. You have this 4 that's going to multiply this guy. So let me put a 4 out in front. And then g of, this is where people tend to make mistakes. So I'm going to just highlight things just to make this clear. You're thinking about what is getting plugged in for x. So don't copy the whole thing. You just want this part right here because this is what's getting plugged in for x. You don't want this right here. So this right here and this right here, those are going to match. But I only want what's getting plugged in for x right there. So it's just going to be this right here inside of brackets. So 1/3 times the quantity, x minus 6. We'll close that down, and then we'll close this down, and then we're done with this. So now let's look at what we have out here, and this is a minus 5. So let's put minus 5 like that. So now we have f of x equals 4 times your g of 1/3 times the quantity x minus 6, and then we have this minus 5. Remember that vertical transformations and horizontal transformations do not impact each other. When you're looking at the order for the vertical transformations, they follow the order of operations. So in this case, you're going to multiply by 4 first. You're going to subtract away 5 second. When you look at the order for the horizontal transformations, you are undoing things, and you have to undo things in the reverse order. So you're going to follow the reverse of the order of operations. If you look at what's inside the brackets here, you have multiplication and then you have parentheses. Well, what I want to do is, with the order of operations, go with parentheses first and then multiplication second. Well, if I'm going in the reverse order, I would want to multiply first and then work inside the parentheses second, and I have to undo things. So I want to undo multiplication by a third. That means I'm going to multiply by 3. And then I want to undo subtraction of 6. That means I'm going to add 6. So hopefully that does make sense. Again, we covered this a lot in graphing transformations, so you can review that lesson if you need to. So I'm just going to number this. Again, you can go left to right if you're putting this in factored form. That's why I spent the time to do this. So this is 1, this is 2, this would be 3, and then this right here would be 4. So starting with this 4 that's multiplying this guy, that's going to give me a vertical stretch by a factor of 4. Then coming inside the brackets, again, we're undoing things. So we're doing this first. So how do I undo multiplication by a third? I want to multiply by 3. So that's going to be a horizontal stretch by a factor of 3. Then I'm going to come on the inside of the parentheses here. How do I undo? Subtracting away 6. Well, I want to add 6. So I'm going to shift 6 units right. Then coming back outside, now I have this minus 5 to deal with. That's very straightforward. I'm just going to shift 5 units down. So looking at a given x comma y on g of x equals 1 over x squared, the corresponding point on f of x, you can have 3x plus 6. Again, you have this horizontal stretch by a factor of 3. That's done first. So you're multiplying by 3. And then you have a shift 6 units right. That's done second. So that's 3x plus 6. Then comma 4y minus 5. Again, that's coming from the fact that you have a vertical stretch by a factor of 4. So you're multiplying by 4 first. And then you're shifting 5 units down. So then you have minus 5 second. So again, I already set up the points just to speed things up. So we have negative 0.5 comma 4. That's going to go to 4.5 comma 11. 0.5 comma 4. That's going to go to 7.5 comma 11. 1 comma 1 is going to go to 9 comma negative 1. Negative 1 comma 1 is going to go to 3 comma negative 1. 2 comma 0.25 is going to go to 12 comma negative 4. And then negative 2 comma 0.25, that's going to go to 0 comma negative 4. Now this is going to be the y-intercept, but I'm going to show you again how to do this by just plugging in a 0 for each occurrence of x. So in other words, just finding f of 0. Now in terms of getting the x-intercepts, this one is a little bit time consuming. So you're going to take your function, set that equal to 0, and you're going to solve. So first we're going to add 5 to both sides of the equation. So we get this 4 over the quantity 1/3 x minus 2 squared is equal to 5. And then I'm going to multiply both sides by this denominator here. And I'm going to get 4 is equal to 5 times the quantity 1/3 x minus 2 squared. So then I get 4 equals 5 times. This comes from expanding that guy. So you get 1/9 x squared minus 4/3 x plus 4. Distribute the 5 into each guy. You get 4 equals 5/9 x squared minus 20/3 x plus 20. And then we're going to subtract 4 away from each side of the equation. And we end up with 5/9 x squared minus 20 over 3x plus 16 is equal to 0. Now I think it's easier to not work with fractional coefficients. So I would multiply both sides of this equation by 9. You would end up with 5x squared and then minus 9 divided by 3 would be 3. 3 times 20 is 60. So this would be 60x. And then plus 16 times 9 is 144. And then this would be equal to 0. So I've written this here just more cleanly. So if I'm going to use the quadratic formula, this is my a, this is my b. Let me go plus negative so that's clear. And this is my c. So I've set this up. So again, a is 5, b is negative 60, and c is 144. We know the quadratic formula, so x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is just me plugging in. You can pause the video if you need it. Essentially, you're going to go through and you're going to end up with this x equals 30 plus or minus 6 times the square root of 5 over 5. So those are going to be your x-intercepts. So the first one, which is going to be 30 plus 6 times square root of 5 over 5. Let me make this bigger here, comma 0. This right here, if you punch it into the calculator, it's about 8.6, let's say 83. I'll just round to the nearest thousandth. The other one is going to be 30, and then you have minus 6 times square root of 5 over 5, and then comma 0. If you punch that into a calculator, I'm going to get about, let's say, 3.317. Just rounding to the nearest thousandth. So if I want the y-intercept, I would just find f of 0. So that would be 4 over. You have 1/3 times 0, and then minus 2. This would be quantity squared, and then minus 5. So this is going to be equal to negative 4. Again, because this down here, this would go away. You'd basically have negative 2 squared, which is 4. 4 over 4 is 1, and 1 minus 5 would be equal to negative 4. So the y-intercept would occur at 0, negative 4. All right, so I've written this out. So the x-intercept, again, this is from the approximations I gave you earlier. So about 8.683, comma 0, and then about 3.317, comma 0. The y-intercept is 0, negative 4. In terms of the vertical asymptote and the horizontal asymptote, you can get these using the traditional method, or you can just use the shift. So if we think about g of x is equal to 1 over x squared, we again have a vertical asymptote, x is equal to 0, and a horizontal asymptote, which is going to be y is equal to 0. What was my horizontal shift? It was 6 units to the right. So that means that the vertical asymptote here would be x equals positive 6. And then what was my vertical shift? Well, I went 5 units down. So that means that my horizontal asymptote would occur at y equals negative 5. All right, so let's look at the graph. So again, I have these points from what we talked about earlier. These have fractions in them, whereas the other ones were decimals. But again, you could just punch this into the calculator. This is going to be 9 halves, comma 11. This is going to be 15 halves, comma 11. Then here you're going to have your 3.317, comma 0. That's one x-intercept. Again, this is approximation. This is 3, comma negative 1. This is 0, comma negative 4. Over here you have, again, your other x-intercept. So 8.683, comma 0. Again, an approximation. This is 9, comma negative 1. And this is 12, comma negative 4. You have your x equals 6. That's your vertical asymptote. And then your horizontal asymptote, which is y equals negative 5. So again, just think about how this is drawn. This guy right here would be drawn to approach that vertical asymptote, which is x equals 6. This guy would come down and it would approach this horizontal asymptote, which is y equals negative 5. Again, the same thing over here. So this guy's going to approach and this guy's going to come down and this guy's going to approach. Now, again, it's not going to touch the horizontal asymptote, which is y equals negative 5 here. Very easy to see because again, you can just say negative 5 is equal to 4 over this quantity 1/3 x minus 2 squared minus 5. If you add 5 to both sides, this right here would be equal to 0. And this can never be 0 because the numerator is 4. For a fraction to be 0, the numerator needs to be 0. The denominator needs to not be 0. So this has no solution. So we can say that this graph would never impact this horizontal asymptote, which is y equals negative 5. All right, let's take a look at problem 4. So we have f of x is equal to the negative of 2 over the quantity x minus 3 squared and then plus 1. Again, I'm going to use graphing transformations here. So we have g of x equals 1 over x squared. So I'm going to write f of x as being equal to, let's just say this is negative 2. So that's coming from this. And then times, you would have your g of, so what is getting plugged in for x? So you have x squared here. And then here you have the quantity x minus 3 squared. So this is going to match up with this. In other words, this right here is what we're going to plug in for x right there. So in the parentheses, we're going to put x minus 3. Then we have this plus 1 on the outside. Let me actually erase this and I'll just circle this. So that's going to come like that. Okay, so coming down here, I've already rewritten this. So f of x equals negative 2 times g of x minus 3 and then plus 1. So again, I'm going to work left to right. So I'm going to say that this is 1, this would be 2, then this would be 3, and then this would be 4. So the negative out in front, that's going to give me a reflection across the x-axis. The 2 right here gives me a vertical stretch by a factor of 2. Coming on the inside, we have x minus 3. Again, to undo that, I want to add 3. So that's going to shift 3 units to the right. That's for this guy right there. And then coming back outside, you have this plus 1. That's going to shift 1 unit up. So thinking about g of x equals 1 over x squared, you have your x comma y, some given point. When you go to f of x, you're going to get x plus 3, comma, negative 2y plus 1. So again, I've already set up the points. So we have negative 0.5, comma 4. That's going to go to 2.5, comma negative 7. We have 0.5, comma 4. That's going to go to 3.5, comma negative 7. We have negative 1, comma 1. That's going to go to 2, comma negative 1. We have 1, comma 1. That's going to go to 4, comma negative 1. We have negative 2, comma 0.25. That's going to go to 1, comma 0.5. And then we have 2, comma 0.25. That's going to go to 5, comma 0.5. If we want to find the x-intercepts, what do? We take our function, we set it equal to 0, and we solve. So negative 2 over the quantity x minus 3 squared plus 1 equals 0. You subtract 1 away from each side, and you get negative 2 over the quantity x minus 3 squared is equal to negative 1. And then what I would do is multiply both sides by this quantity x minus 3 squared to clear the denominator. So I get negative 2 is equal to the negative of the quantity x minus 3 squared. Here, what I would do is divide both sides by negative 1. So this would cancel with this, and this would cancel with this. So you're going to get 2, let me write this up here. You're going to get 2 is equal to the quantity x minus 3 squared. So if we use the square root property on this, we can say that x minus 3, that's what's inside here, is equal to plus or minus the square root of 2. So then if we just add 3 to both sides, you would have, let me write that over here, you would have x is equal to plus or minus the square root of 2, and then plus 3. So that splits up into x equals the square root of 2 plus 3, or x equals the negative of the square root of 2 plus 3. So this one, if you think about square root of 2 plus 3, comma 0, if you punch that into the calculator, you're going to get about, let's say 4.414. We'll just round to the nearest thousandth, like we did before. Let me fix that. And then the other one, you're going to have negative square root of 2 plus 3, comma 0. Let me fix that, and let me fix that. Let's punch this into the calculator, and I get about 1.5 h, and then let's just say 6, we're going to round to the nearest thousandth. All right, in terms of finding the y-intercept, remember we're going to look at f of 0. So this would be equal to the negative of 2 over, you'd have the quantity 0 minus 3 squared, and then plus 1. If you do the math here, you're going to end up with 7/9. And that's just because you can move this negative up here. You could say this is negative 2 over. 0 minus 3 would be negative 3, and then negative 3 squared would be 9. If you add this to 1, you could write that as 9 over 9. And of course, this becomes negative 2 plus 9, which is 7, over the common denominator of 9. So the y-intercept is going to occur at 0, 7/9. So coming down here, again, we have our x-intercepts. So 1.586, 0, and then 4.414, 0. So again, just approximating those. The y-intercept is 0, 7/9. The vertical asymptote and the horizontal asymptote, again, you can just get those from the shifts. So we have our g of x is equal to, again, 1 over x squared. So the vertical asymptote, that is x is equal to 0. And the horizontal asymptote, that is going to be y is equal to 0. So what was the horizontal shift? Well, we went 3 units to the right, so that means the vertical asymptote is now going to be at x equals 3. What was the vertical shift? Well, we went 1 unit up, so now the horizontal asymptote is going to be at y equals 1. All right, let's come down to the graph. So again, we have f of x equals the negative of 2 over the quantity x minus 3 squared, and then we have plus 1. So looking at the points, we know we have 0, 7/9, we have 1, 1/2, then we have 1.586, remember that's an approximation, 0, then we have 2, -1, and then coming down here we have 5 halves, -7. Jumping to the other guy, we have this 7 halves, -7, we have this 4, -1, we have this 4.414, 0, again that's an approximation, and then we have 5, 1/2. So that's all the points we got. You can do more if you need to. Then this guy right here, the vertical asymptote, that's going to be x is equal to 3. So that guy right there. The horizontal asymptote is going to be y equals 1. So of course, when you sketch this piece is going to come down and approach that vertical asymptote. Again, x equals 3. So we have this coming like this, and it's drawn to approach that horizontal asymptote of y equals 1. It's not going to touch. And again, I'll show you that in a moment. Same thing for this piece over here. This part is going to approach that horizontal asymptote, which is y equals 1, but not touch it. And then coming down here, this is going to approach that vertical asymptote, which is x equals 3, but not touch it. Okay, so to prove that this graph is not going to intersect that horizontal asymptote, y equals 1, again, you could just plug in a 1 right there and say 1 is equal to -2 over your quantity x minus 3 squared, and then plus 1. If you subtract 1 away from each side of the equation, you're again left with this -2 over the quantity x minus 3 squared is equal to 0. And this equation, as we've talked about before, does not have a solution. Because for a fraction to be 0, again, the numerator needs to be 0 and the denominator needs to not be 0. The numerator here is always going to be -2, so this guy has no solution. So you can say that the graph here is never going to intersect this horizontal asymptote, which is y equals 1. All right, let's take a look at problem 5. So we have f of x is equal to x cubed minus x squared over x minus 1. So this is going to be one where you can factor and cancel. So let me just start by factoring the numerator. I'm going to pull out an x squared. So inside the parentheses, you would have x minus 1. And then down here, you have your x minus 1. Now, before I cancel a common factor of x minus 1 like that, just think about the fact that when you do that, you're going to end up with just x squared, and that's defined for all real numbers. So that's your domain there. But with the original rational expression, x can't be 1. So we have to make sure we carry that over. So what I usually do is before I cancel, you could write out the domain or something like that if you want. You could say, well, x minus 1, where's that equal to 0? Add 1 to both sides. This cancels, you get x is equal to 1. So you could write right here that the domain is the set of all x such that x is not equal to 1. And then it's clear when you cancel this with this, that this restriction needs to carry itself over. So now the simplified version of this is f of x equals x squared, but you're going to say for x is not equal to 1 because we're carrying that restriction over. When you graph this guy, we know what the graph of f of x equals x squared looks like. You're not going to have any asymptotes. We know that the x-intercept and the y-intercept, those are both going to occur at the point 0, 0 or the origin. And we have our 0, 0. Again, that's your x-intercept and your y-intercept. Your -1, 1, your -2, 4, your -3, 9. Normally you have 1, 1. I'll talk more about that in a second. You have your 2, 4, and your 3, 9. So this graph right here for f of x equals x squared, for x is not equal to 1, is the same as f of x equals x squared, except where x is 1. Where x is 1, what you want to do is draw yourself a little hole right there, just to make it clear that this function right here is not defined at an x value of 1. All right, let's look at problem 6. So we have f of x is equal to 2x cubed minus 3x squared plus x over x squared minus 3 halves x plus 1 half. So what we're going to do for this problem is just manipulate it to where we can see what we can cancel. So down here, you're going to see we can cancel this with this. But before we do that, let's first look at the numerator. And we can see that we have x cubed, we have x squared, and then x. So let's pull out an x, and that's going to give us x times the quantity, 2x squared minus 3x plus 1, over this x squared minus 3 halves x plus 1 half. So then I'm going to multiply by 2 over 2, which again is just 1, so that's completely legal. And so I'm going to put this 2 out here. So you'd have 2x times the quantity 2x squared minus 3x plus 1, and this would be over. If I distribute this 2 to each guy, you're going to get 2x squared minus 3x plus 1. So again, it's obvious once you take these steps that you can cancel this with this. But before you do that, you want to figure out what are the restricted values for the original rational function. So what would give me division by 0? Let me put a little border here. And let me factor this. So this is 2x squared minus 3x plus 1. And let's say that's equal to, let me put up some parentheses here. So you'd have 2x here and x here. This 1 right here is only going to come from -1 times -1 or +1 times +1. Because this is a negative right here, it's going to come from -1 times -1. So if you check this, the outer is -2x. The inner is -x, -2x minus x, that's -3x, so this is good to go. All right, so what I would do is I would take this right here, which is going to be the denominator. Let me actually just rewrite this. Let me say this is equal to, and I'll slide down a little bit. So 2x times the quantity, 2x minus 1, times the quantity, x minus 1. So then let's match that down here. We're going to have this 2x minus 1, and then we're going to have this x minus 1. So again, that's just factoring this right here, and you have this 2x out in front, so that's why it's right there. Okay, so we're going to take the denominator, set it equal to 0, and solve. That's all we need to do. So we're going to say that the quantity 2x minus 1 times the quantity x minus 1 is equal to 0. So that turns into 2x minus 1 equals 0, or x minus 1 is equal to 0. So this one you would add 1 to both sides of the equation, and then this would cancel. You get 2x is equal to 1. Divide both sides by 2, and this cancels. You get x is equal to 1 half. Over here, we're going to add 1 to both sides of the equation. We're going to cancel this, and we're going to get that x is equal to 1. So if you think about the domain for the original rational function, let me put this over here. So the domain, we would say, it's the set of all x such that x is not equal to 1 half, and then also it can't be 1. So those two values would make the denominator 0. Now, when you go through and you cancel, so in other words, if you cancel this with this and this with this, you end up with f of x equals 2x. So the domain for this guy is all real numbers, but again, you've got to carry those restrictions over. So I'm going to say this is f of x equals 2x, but for x is not equal to 1 half, and then also 1. So for the asymptotes for this, again, we're just thinking about f of x equals 2x. You would just have a hole at x equals 1 half and then x equals 1. But your asymptotes, you would not have any for that. This is just us graphing a linear equation in two variables. So for the x-intercept and the y-intercept, those are both going to occur at the origin, so 0, 0. So coming down to the graph, so you would sketch f of x equals 2x, but where x is 1 half, and then also where x is 1, you're going to put a little hole in the graph. So right here, you have -2, -4, 0, 0, and 2, 4. And this right here would be 1 half, 1 normally. You're going to put a hole there because this function is not defined where x is 1 half. And then normally this would be 1, 2. But again, you're going to put a hole there because this function is not defined where x is 1. All right, so for the rest of the problems, we're going to use this procedure from the lesson where we have graphing a rational function and we're given f of x equals p of x over q of x, where q of x, this guy in the denominator, is not 0. P of x and q of x are polynomials, and the rational expression is in lowest terms. So that's actually important. You want to make sure that this guy is in lowest terms before you start this procedure. If it's not in lowest terms, in other words, if it's not simplified, you want to factor your numerator and denominator and then cancel any common factors between the numerator and denominator, and then take note of any holes that you're going to have in your graph before you start this procedure. So the first thing you'd want to do is find and sketch all asymptotes. The second thing is to find the x and y intercepts. So we know the y-intercept occurs at 0, f of 0. Then the x-intercepts occur at k, 0, where k is the 0 of the numerator. The third thing here is to determine whether the graph will intersect its non-vertical asymptote, so that's if it exists. The fourth thing is to split the number line up into intervals based on the x-intercepts and vertical asymptotes. Then you're going to pick an x value in each interval, then find and plot the related point. For some functions that works, you can just use one point. In other cases, you're going to need to use more than one point just to get a better idea of what the graph looks like. So this would be on a case-by-case basis. And then the fifth and final thing here, we're going to sketch the graph. Remember, this is just going to be a rough sketch. It does not need to be perfect. All right, let's take a look at problem 7. So here we have f of x is equal to 2x squared over x squared plus x minus 6. So this guy right here is simplified. So I want to move into my procedure. And the first thing is going to be to find the asymptotes. So how do we find the vertical asymptotes? We're going to take this denominator, which is x squared plus x minus 6. We're going to set that equal to 0, and we're going to solve. So to speed things up a little bit, I've already done this for us. So we have x squared plus x minus 6 equals 0. This left side right here can be factored. Again, you're looking for two integers whose sum is 1 and whose product is negative 6. So those two integers would be negative 2 and positive 3. So the left side can be factored into the quantity x minus 2 times the quantity x plus 3. And of course, we set this equal to 0, and we could solve this with the zero product property. So this first factor right here, this x minus 2, set that equal to 0, and then solve that. You add 2 to both sides, you get x equals 2. Then or, you're going to take the second factor here, this x plus 3, set that equal to 0. We would subtract 3 away from each side, and we get x equals negative 3. So your two vertical asymptotes are going to be x equals 2, and then also x equals negative 3. So just coming down here, this is your x equals negative 3, and then this is your x equals 2. So those are your two vertical asymptotes. All right, coming back up, we also need to find the horizontal asymptote. So we want to look at the degree of the numerator, which in this case is 2, and the degree of the denominator, which in this case is also 2. So when the degree of the numerator is exactly the same as the degree in the denominator, we know that we say y equals the ratio of the leading coefficients. So in this case, it's y equals 2 over 1, which is y equals 2 for the horizontal asymptote. So coming down here, this is our y equals 2. Again, that's going to be the horizontal asymptote. All right, so the next thing is we want to find the intercepts. So to find the x-intercepts, you're going to take your function, so 2x squared over x squared plus x minus 6, set that equal to 0, and solve. So as I've said many times, a fraction is going to be 0 when the numerator is 0 and the denominator is not 0. So take your numerator, in this case, that's 2x squared. So 2x squared, and set that equal to 0. And we're just going to solve that. So divide both sides of the equation by 2. And of course, this would cancel. And then we're going to have x squared is equal to 0 over 2 is 0. And the solution here is just going to be that x is equal to 0. So this means that the x-intercept is going to occur at 0, 0. But there's actually something very important here. Notice that this is squared. So that tells me that the 0 of the number 0 has a multiplicity of 2, which is an even multiplicity. Well, since this guy has an even multiplicity, at 0, 0, we're going to touch the x-axis and turn around. So coming down here, this is your 0, 0. That's going to be your x-intercept. It'll also be the y-intercept, but we'll talk about that in a moment. You have this point right here, which is negative 2, negative 2, and this point right here, which is 3/2, negative 2. I'll talk about where that's coming from in a little while. For right now, we're just going to use this to understand this concept. What's going to happen is this guy is going to come up, and again, at 0, 0, we're going to touch the x-axis, and we're going to turn back around. The reason that's helpful here is that when you're doing these types of problems, one of the hardest things is getting the turning points, and that's because we don't know calculus yet. When you get into a calculus class, after you learn about derivatives, you're going to have a section on curve sketching where you're going to do this stuff again, but you're going to go into more detail. So at that point, you're going to understand how to find all the turning points. For right now, we're stuck with just doing an estimation procedure. But in this particular case, we're going to luck out because that's going to be our turning point there. In terms of the y-intercept, let me get rid of this. All you're going to do is figure out what is f of 0. And in this case, that's equal to 2 times 0 squared over, you have 0 squared plus 0 minus 6. So this becomes 0 over negative 6, which equals 0. So the y-intercept occurs at 0, 0. All right, the next thing we want to do is figure out, will the graph intersect our horizontal asymptote? So remember that the horizontal asymptote is the line y equals 2. So with a horizontal line, it does not matter what the x value is, the y value is always the same. In this case, the y value is always going to be 2. So to figure this out, you're going to take your function, 2x squared over x squared plus x minus 6, and set it equal to 2. So you're trying to find the x value for which the y value is 2. In other words, the x comma y, or the point where y is 2, that's going to be a point of intersection with this line, y equals 2. So what we would do to figure this out, we would multiply both sides by the denominator here. So x squared plus x minus 6, just to clear it, that's going to give me 2x squared on the left, is equal to, on the right, you have 2 times the quantity x squared plus x minus 6. I'm just going to divide both sides of the equation by 2, just to get rid of that and make it a little bit simpler. So this would cancel with this would cancel with this. I'm going to have x squared is equal to x squared plus x minus 6. Of course, you can subtract x squared away from each side of the equation. So this would cancel, this would cancel. Let's put a 0 over here. And so you would have x minus 6 is equal to 0. Let's add 6 to both sides of the equation, and this would cancel, and you're going to have that x is equal to 6. So in other words, we're saying that 6, 2, that's going to be your point of intersection with this horizontal asymptote, y equals 2. All right, coming down here, this is going to be your 6, 2. So that's your point of intersection with your horizontal asymptote, y equals 2. The reason this is important to figure out is that when you draw this piece over here, you're going to have something that looks like this. So this would approach, again, this is your vertical asymptote. So we're approaching this, and then we're coming down, 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 and we're going to approach that horizontal asymptote, y equals 2. But I want you to notice that for this piece right here, you're going to actually stay above the horizontal asymptote, y equals 2. You're not going to cross through because you only cross through right there. Let me show you what this looks like on Desmos. Again, you can click the link. So this is the piece right here that I was working with. So we're coming down, down, down. We're going to be approaching this horizontal asymptote, y equals 2. That's the dashed green horizontal line there. We're approaching that, but we're never actually going to touch it. Notice that we're staying above that. Let me zoom in a little bit for you. So we're staying above that, above that, above that. So that's really important if you're trying to make an accurate graph. When we look at this piece over here, it's going to be different. We need to draw it to where we actually cross through right here. And what's going to happen is we're going to come down, we're going to hit a local minimum point. And again, you need calculus to figure that out. But essentially after that, we're going to start coming back up and we're going to approach this line y equals 2, but from below it. So in other words, it would look something like this. So again, this won't be perfect, but something like this. So we're going to come down, come down, come down. And then let's just say that we're going to cross through right there. And then we're going to come down like this. And again, we're going to be approaching this line y equals 2, but from below it. Let me just come back here and I'm going to show you the other piece. Let me just zoom in. And so if you look at this piece, again, you're coming down, coming down, coming down. You cross through that horizontal asymptote at 6, 2. Then you're going to be below that, and you're going to be coming down to where you have this local minimum point, which is 12, 1.92. Again, at this level, we don't know how to get that. You need some calculus, but it's not that important. You're trying to make a rough sketch. Just make sure you note that you're crossing through there. And then this guy, again, as x increases without bound, or as x approaches positive infinity, this guy is going to approach that horizontal asymptote, y equals 2, but notice that it's doing it from below, whereas on the other side, it's doing it from above. So the only way you would figure that out is if you get this point of intersection here. So you know that this is going to cross through, and then it's going to do like this. Whereas on the other side, we know that it's not going to cross through, so it's going to stay above. Okay, so now let's just put everything together. So the vertical asymptotes, we know those are x equals -3 and x equals 2. The horizontal asymptote is y equals 2. The x-intercept and the y-intercept are both going to be at 0, 0 or the origin. And then what you're going to do is you're actually going to split the number line up into intervals. Again, you're using the x values from your x-intercept, in this case that's 0, and also from the vertical asymptotes, so -3 and then 2. So you would have anything less than -3, anything between -3 and 0, anything between 0 and 2, and then anything greater than 2. Again, if you get lost by what I did, just go to your coordinate plane, and you should already have your vertical asymptote. So you should have that one there, and then this other vertical asymptote there, and then your x-intercept. And just think about the intervals you're creating. Again, just look at the x-axis. You have anything less than -3, you have between -3 and 0, then between 0 and 2, and then anything greater than 2. So that's what I'm doing there. So coming back up, you're going to pick an x value in each interval, plug it in, and get the y value, so that gives you a point. So in this interval, I have -6, 3. In this one, I have -2, -2. In this interval, I have 1.5, -2. And then in this interval, I have 3, 3. Now, I'm just going to tell you, in a lot of cases, you do need to get additional points. So I've put some here. We figured out 6, 2 earlier. That's where we're going to intersect that horizontal asymptote, y equals 2. But these are just additional points here that I came up with to help with the graph. So -4, 16 thirds, and then 12/5, 16 thirds. Then I have two things here that, again, in most situations, it's going to require calculus to figure out. So we have a local maximum point at 0, 0. Again, we were able to get this here because the 0 associated with our x-intercept, which happened to be the number 0, had an even multiplicity. So we would touch and turn around there. So we were able to find this local maximum point. But in most cases, you need calculus to get that exact point. The local minimum point, which again, this is something you would use calculus for, this is 12, 48 over 25, which this is going to be 1.92 as a decimal. Again, that's something I showed you earlier when we went to Desmos. So coming back down here, let me just show you everything. So this is -4, 16 thirds. thirds. This is negative 6 comma 3. This is going to be negative 2 comma negative 2, 0 comma 0, 3 halves comma negative 2, 12 fifths comma 16 thirds, 3 comma 3, and 6 comma 2. In order to sketch the graph, again, you're just going to take all the information and just put it together. I know that this guy, again, you have a vertical asymptote at x equals negative 3, so this is going to shoot up like this right there. And because the 0 that's associated with creating this x equals negative 3 vertical asymptote, because the multiplicity of that guy was odd, I know that if this goes up like this is coming down like this. And of course, this is going to continue like this, and it's going to approach that horizontal asymptote, which is y equals 2. But it's going to stay above that line, right? So it's above that. It's never going to intersect over here. Then for this piece right here, this is going to shoot up like this. And so again, because the 0 that's associated with creating that x equals 2 vertical asymptote has an odd multiplicity, this is going to come down like this. So that's our behavior. And so this is going to go like this. And in this particular case, it's going to cross through. And again, we're going to come down. And eventually we're going to come back up and approach that line y equals 2. It's only going to cross right here. After it crosses through, it's not going to touch it again. Now, this piece right here, again, we found earlier, because this is going to touch here and turn around. So I know this is very time consuming and tedious, but just something you have to get used to if you're going to graph these guys. As you get into calculus, and again, you get to that section on curve sketching after derivatives, you'll be able to make a more accurate graph because you'll be able to find the local minimum and maximum points. So this is our computer generated version. Again, you can click that link for Desmos, the one I showed you earlier. This is f of x equals 2x squared over x squared plus x minus 6. So again, just like I said, this is going to come up like this. And so this is going to come down like this. And this right here is going to come down through those points and approach that line y equals 2, but we're going to stay above it. This right here is going up like this. So that means this is coming down like this. And this right here is going to come down, come down, come down. It's going to cross through. And again, once it crosses through, you can again, look at this guy on Desmos. You see how it crosses through at 6 comma 2, and then we're going to be below that line y equals 2. It's going to hit a local minimum point right there at 12 comma 1.92. And after that, it's going to start coming back up and approaching that line y equals 2 from below it. Now on this part right here, again, we know that there's a turn, and we're going to hit right there at 0 comma 0. We're going to touch the x-axis and turn around. So with the scale of things, it's kind of hard to see everything. So again, just click that link on Desmos so you can get more detail. All right, for problem 8, we have f of x is equal to x squared minus 3x plus 2 over 4x plus 4. So this guy is going to be simplified. And so what we want to do is look for the asymptotes. For the vertical asymptotes, in this case, you would just have one single vertical asymptote. You're going to take your denominator, which is 4x plus 4. You're going to set that equal to 0, and you're going to solve. So we would subtract 4 away from each side of the equation. You get 4x equals negative 4. Divide both sides of the equation by 4. You're going to get x equals negative 1. So just coming down here to show you things as I do them, this right here is going to be your vertical asymptote, which is x equals negative 1. Now you'll notice that I've drawn in a slant asymptote. Where does that come from? Well, coming back up here, remember the rule for finding a horizontal asymptote. If the degree of the numerator, which in this case that's going to be a 2, is greater than the degree of the denominator, in this case that's going to be a 1, then you will not have a horizontal asymptote. But if you have the case where the degree of the numerator is exactly 1 more than the degree of the denominator, so here this is 2 and this is 1, you will have a slant or oblique asymptote. And the way you figure that out is through long division. So you're going to take this and divide it by this. Now, we would like to use synthetic division, but you need your divisor to be of the form x minus k. This 4x plus 4 does not qualify for that. So you can use polynomial long division, or you can change the form of this. Either way is acceptable. So whatever you want to do here. I would do synthetic division. It's a little bit faster. And all you have to do is multiply this by 1/4 over 1/4. Remember, this is just 1, so we're not doing anything illegal. So this would turn into 1/4 x squared minus 3/4 x plus 1/2, and this is over x plus 1. When you make this change, remember that this is your denominator now. So whatever remainder you have for this problem, it has to go over this and not this. So that's a big thing when you change this over. So looking at this, again, we have f of x equals 1/4 x squared minus 3/4 x plus 1/2. This is over x plus 1. So we're going to change this into x minus a negative 1. And so negative 1 goes right there. And then you're just going to grab your coefficients. So 1/4 goes here, negative 3/4 goes here, and then 1/2 goes here. So then we can just do our synthetic division. So drop this down. Negative 1 times a fourth is negative 1/4. Negative 3/4 plus negative 1/4 is negative 1. Then negative 1 times negative 1 is positive 1. And 1/2 plus 1 is 3/2. So the way you write this right here is you take this as the coefficient for, again, you're going to drop this by 1 degree. So if this is x squared, you want x to the first power. So this is just 1/4 x. Then this would be your constant. So let's write minus 1. And again, here's where you have to be very, very careful. The denominator you're working with in this problem is now x plus 1. it's not 4x plus 4 anymore. So we have to use this denominator when we write our answer. So we want to put that it's going to be plus, you have this 3 halves here, so 3 halves, and that would be over this x plus 1. You could write it as x plus 1 over 1 like that. You would have 1/4 x minus 1. Let me move this down just a little bit so it will fit. And then plus, we would take this guy, this 3 halves, and multiply by the reciprocal of this. So 1 over your x plus 1. And so this turns into 1/4 x minus 1, and then plus 3 over 2 times the quantity x plus 1. Okay, let me get rid of this. We're going to just take this part right here. So the slant asymptote is going to be y equals 1/4 x minus 1. The reason for that is that this part right here is going to go to 0 as x approaches positive infinity or negative infinity. So you're just going to have this right here. So coming down here, this is going to be your slant asymptote. So this is the line y equals, you could say 1/4 x or 0.25x and then minus 1. All right, the next thing we want to do is find the intercepts. So if we want to find the x-intercepts, you take your x squared minus 3x plus 2 over 4x plus 4, set that equal to 0, and solve. So once again, we know that this would be 0 if the numerator is 0 and the denominator is not 0. So just take your numerator, so x squared minus 3x plus 2. Set that equal to 0. And so this can be solved using factoring. So if we think about two integers whose sum is -3 and whose product is +2, well, that would be -2 and -1. So you get x minus 2, that quantity, times the quantity x minus 1. And of course, this is set equal to 0. And so to solve this, you just use your zero product property. So you're going to say that x minus 2 is equal to 0. Let me fix this x here. Then or x minus 1 is equal to 0. For this one over here, you just add 2 to both sides of the equation. This cancels. You get x is equal to 2. And then for this one over here, we would add 1 to both sides of the equation. This cancels. You get x is equal to 1. So that means you're going to have x-intercepts at 2, 0 and 1, 0. Now keep in mind that the multiplicities here are going to be 1 in each case. So that means it's an odd multiplicity. So we're going to cross through the x-axis at 2, 0 and 1, 0. So let me come down here. This is your 1, 0 and your 2, 0. So that means that this guy is going to cross through right here at 1, 0, come down, and then it's going to cross back through at 2, 0. Again, this is kind of hard to see with the scale of what I've given you. So I have that Desmos link. This is going to be important for your graph. Let me zoom in a little bit. This is your 1, 0. So we're crossing through the x-axis there, and then we're coming down, and then we're going to cross back through the x-axis at 2, 0. Again, you can use that link that I gave you to zoom in and see that. All right, additionally, we want to find the y-intercept. So you want f of 0. So this is equal to 0 squared minus 3 times 0 plus 2 over 4 times 0 plus 4. So you end up with 2 over 4, which is 1/2. So the y-intercept would be at 0, 1/2. So that's going to be this guy right here. All right, so the next thing we want to do is figure out, is our graph going to intersect the slant asymptote? So remember, the slant asymptote is y is equal to 1/4 x minus 1. So what we're going to do is we're going to take our function, so x squared minus 3x plus 2 over 4x plus 4, and we're going to set it equal to this guy right here, so this 1/4 x minus 1. So we're going to clear the denominator by multiplying both sides by 4x plus 4. So that's going to give me x squared minus 3x plus 2 is equal to the quantity 4x plus 4, so that's coming from the denominator here, times the quantity 1/4 x minus 1, so that's coming from this right here. So let me just copy this. This is x squared minus 3x plus 2 is equal to, so first terms, 4x times 1/4 x. 4 times a fourth is 1. X times x is x squared. The outer, you'd have 4x times -1, that's minus 4x. The inner, you have 4 times a fourth, that's 1, then times x. So this is just plus x. And then the last, you have 4 times -1, that's -4. So -4x plus x, that's going to be -3x. So let me just erase this and put -3x like this. So now you have x squared minus 3x plus 2 is equal to x squared minus 3x minus 4. And you're going to see that if you subtract x squared away from each side, this is going to go away and this is going to go away. If you add 3x to both sides, this will go away, and this will go away, and you'd be left with 2 is equal to -4, which is a false statement. So when we see this, we know that we have no solution for our equation. So what that means is that when we draw this guy, we're not going to impact that slant asymptote. So this guy is drawn to approach, but not touch over here, and this guy is drawn to approach, but not touch over here. All right, so let's just put everything together. So we know we have a vertical asymptote that's going to be x equals -1. And again, the multiplicity of the 0 associated with that was 1, so that's odd. So when you're looking at that, if this guy's going up like this, that means this guy's coming down like this. Then we know we have a slant asymptote, which is y equals 0.25, or you could say 1/4 x minus 1. The x-intercepts are going to occur at 1, 0 and 2, 0. And again, we're going to cross through the x-axis at each one of those. The y-intercept occurs at 0, 0.5, or you could say 0, 1/2. Again, splitting the number line up into intervals, just using this x value here, this x value here, and this x value here, you get anything that's less than -1, between -1 and 1, between 1 and 2, and then anything greater than 2. Again, that's coming from the fact that we're using this, and this. So anything less than -1, anything between -1 and +1, anything between 1 and 2, and then anything greater than 2. So that's where that's coming from. All right, so in this first interval, I'm going to pick -3 for the x value, and I'm going to get a y value of -2.5. Then in this interval, I'm going to have -0.5, 1.875. In this interval, I'm going to have 1.5, -0.025. And then in this interval, I'm going to have 3, 0.125. Now, these guys are going to be kind of hard to see on the graph given the scale. So again, I'll just go to Desmos and show you that. You can just click on that link. If you need to get more detail, you can always just zoom in. So some additional points. This is just for us to get a better sketch. So -6, -2.8, -2, -3, -1.5, -4.375. So coming down here, I have everything listed with fractions. Again, you could just use your calculator to put it back into decimal form, or you can just look at Desmos, it does it for you. So this is -1/2, 15/8. This is 0, 1/2, 1, 0, 2, 0, and 3, 1/8. Then over here, we have -6, -14/5, -3, -5/2, -2, -3, and then -3/2, -35/8. So again, just thinking about the behavior of things, just to get an idea of what this graph is going to look like, we know that this is going to shoot up like this. And so that means this is going to shoot down like this. Again, I know that because the multiplicity of the 0 associated with that vertical asymptote was 1. And so it's an odd multiplicity. So it goes up and then it comes down. Then this guy right here is going to come down like this. And this is actually important. We're going to cross through the x-axis at 1, 0. So we're going to be below the x-axis. And then we're going to cross back through the x-axis at 2, 0. And we're going to be above the x-axis. And we're going to do like this. And we're going to approach that slant asymptote, which is y equals 0.25x minus 1. All right, then this piece right here, we're going to have this little curve like this. And again, this is drawn to where it approaches, but does not touch that slant asymptote, which is y equals 1/4 x minus 1. So just verifying things with the computer-generated version, we have f of x equals x squared minus 3x plus 2 over 4x plus 4. So again, this right here is shooting up like this. It's going to approach that vertical asymptote, which is x equals -1, but not touch it. It's going to come down, come down, come down. And when we get to this 1, 0, this x-intercept, we're going to cross through the x-axis. We're going to come down. And then when we get to this x-intercept 2, 0, we're going to cross back through. So we're going to be above the x-axis again. And then this guy is going to, again, approach that slant asymptote, y equals 1/4 x minus 1. This piece right here, again, because this is shooting up, this is going to shoot down. And again, approach that x equals -1. We're going to have this curve right here. And then basically this is going to be drawn to where it approaches this y equals 1/4 x minus 1, but doesn't touch it. All right, for problem 9, we have f of x is equal to x squared minus 2x minus 15 over the quantity x minus 1 times the quantity x minus 2 times the quantity x plus 3. So this is one that we can actually simplify. So let's go ahead and factor the numerator. We don't have to factor the denominator because that's been done for us. But we want two integers whose sum is -2 and whose product is -15. So that's going to be -5 and +3. So let's say this is the quantity x minus 5 times the quantity x plus 3. This would be over. You have your quantity x minus 1 times your quantity x minus 2 times your quantity x plus 3. Now, before we cancel a common factor of x plus 3 between the numerator and the denominator, what we have to consider is that when we simplify this guy, we're removing the x plus 3 from the denominator. So that means the restriction that's created from this factor of x plus 3, so let's say x plus 3 is equal to 0, we need to figure out what that's going to be. So let's subtract 3 away from each side of the equation. This cancels. You get x equals -3. So what we're going to say, let's just come down here. Well, we cancel this with this. So when we cancel a common factor of x plus 3 between the numerator and denominator, we end up with this simplified form here. So f of x is equal to x minus 5 over the quantity x minus 1 times the quantity x minus 2. But we have to say for x is not equal to -3, because in the original rational expression, x was not able to be equal to -3 because that gave me division by 0, which again is undefined. So you have to carry that restriction over. So this right here is going to create a hole in your graph. And the way you figure out where that's going to be, you would just say f of -3, and this equals, you'd plug in -3 right there for x, so then -5 over, this would be -3 minus 1, that quantity, times the quantity -3 minus 2. Let me fix this. So this would be equal to negative 3 minus 5 is negative 8. And this is over. Negative 3 minus 1, that's negative 4. Let's write negative 4. And then negative 3 minus 2, that's going to be negative 5. So negative 8 divided by negative 4, that would be positive 2. So you have 2 over negative 5, so that is negative 2/5. So the whole is going to occur at negative 3 comma negative 2/5. So just coming down here, it's kind of hard to see, but I wrote whole here. So it's going to be right there at negative 3 comma negative 2/5. I also wrote it right here. So I'm going to be talking about this later on. So you see where I wrote whole, negative 3 comma negative 2/5, just something you want to note when you're making your graph. All right, so now that we have the simplified form and we know where the whole is going to be in the graph, we can move on to our procedure. So we want to find the asymptotes. So again, just take your denominator. So the quantity x minus 1 times the quantity x minus 2, set that equal to 0 and solve. That's how we're going to find the vertical asymptotes. So of course, this turns into x minus 1 equals 0 or x minus 2 equals 0. And we solve that by adding 1 to both sides of the equation over here. That gives me x equals 1. And adding 2 to both sides of the equation over here. That gives me x equals 2. So you can have a vertical asymptote at x equals 1. And then another vertical asymptote at x equals 2. So coming down here, this is your vertical asymptote at x equals 1. And then this is your vertical asymptote at x equals 2. Then for the horizontal asymptote, the degree of the numerator is 1. The degree of the denominator is going to be 2. If that's not obvious to you, you can just do FOIL here. So x times x is x squared. The outer would be negative 2x. The inner would be negative x. The last would be negative 1 times negative 2. That's positive 2. Combined like terms here, this is x squared minus 3x. And then plus 2. So the main thing is to look at the degree of the numerator, which is 1, and the degree of the denominator, which is 2. And if the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote, which is the x-axis, or the line y equals 0. Now, as I told you before, if I have the x-axis as a horizontal asymptote, I do not label it. But for your graph, if you want to, you can go like that and just say, this is the horizontal asymptote, so it's going to be y equals 0. You can put it there. You can make a dashed line if you want. That's going to be personal preference. All right, the next thing we want to do is to find the intercepts. So let's take this x minus 5 over the quantity x minus 1 times the quantity x minus 2, set that equal to 0 and solve. So that will allow us to get the x-intercept in this case. And so again, if you want a fraction to be equal to 0, the numerator needs to be 0 and the denominator needs to not be 0. So take your numerator, x minus 5, set that equal to 0 and solve. You add 5 to both sides, you get x equals 5. Now the multiplicity of this 0 is 1, which is odd. So that means at 5 comma 0, we're going to cross through the x-axis. Why is that important? Well, let me show you this on this Desmos graph. It's going to be kind of hard to show you on the other one. So I'm going to zoom in. Again, you can just click that link. So we're going from below the x-axis to above the x-axis. And what's going to happen is we're going to sit on top of the x-axis. And as the x values go out to positive infinity, we're going to approach this line y equals 0 or the x-axis. We're approaching that horizontal asymptote, but we're not going to touch it. But the main thing is that we're above the x-axis the whole time there. So over here on this other piece, you're going to stay below the x-axis. And again, that's because there's no point of intersection over here with the x-axis or that line y equals 0, the horizontal asymptote. Again, this plays a big part into sketching the graph more accurately. Now, in terms of your y-intercept, again, you just find f of 0. So f of 0 will be equal to 0 minus 5 over the quantity 0 minus 1 times the quantity 0 minus 2. So this equals, up here you'd have negative 5. Down here you'd have negative 1 times negative 2, which is positive 2. So negative 5 over positive 2, that's going to be negative 5 halves. So 0 comma negative 5 halves, or you could say 0 comma negative 2.5 if you want. That's going to be your y-intercept. So just coming down to this graph, this is your 5 comma 0, your x-intercept, and then this is your y-intercept, 0 comma negative 5 halves. All right, let's come down to this little page here where I have all the information. So for the vertical asymptotes, again, it's x equals 1, and then also x equals 2. We know the multiplicity of each 0 associated with forming those vertical asymptotes is going to be 1. That's an odd multiplicity, so we know that behavior. The horizontal asymptote is y equals 0, or the x-axis. We know that we're going to impact that at your x-intercept, which is 5 comma 0. The whole in the graph is at negative 3 comma negative 2/5. The y-intercept is 0 comma negative 5 halves. And again, you just split your number line up into intervals based on this, and this. Your x values from your vertical asymptotes, so 1 and 2, and then your x value from your x-intercept, so 5. So you want anything less than 1, anything between 1 and 2, anything between 2 and 5, and then anything greater than 5. Again, like I said before, if you get confused by that, just go to your little coordinate plane and highlight things and just say, okay, I want anything less than 1, anything between 1 and 2, anything between 2 and 5, and then anything greater than 5. So coming back up, again, we're just going to pick something in each interval, plug it in and see what we get. So I have -2 comma, -0.583, where that 3 is going to repeat forever. Then in this interval, I have 1.25 comma 20. In this interval, I have 2.6 comma -2.5. In this interval, I have 6 comma 0.05. And then I have some additional points to make it easier to graph. So 0.75 comma -13.6, 1.4 comma 15, 1.8 comma 20, and then 1.6 where the 6 repeats forever, comma 15, and then 2.176 comma -13.6. Then again, when we look at this local minimum point and the local maximum point, you need calculus to get these. This right here, you really don't need for your graph at this point. You would need it when you get to curve sketching and calculus, but for right now, you can forget about it. This right here, you need to know where this guy is going to turn right here. But again, you can use an estimation procedure like we talked about before. So just coming down here and thinking about what we have, this is your 5/4 comma 20. This is your 9/5 comma 20. This is your 7/5 comma 15. This is your 5/3 comma 15. This is your -2 comma -7/12. This is your 0 comma -5/2. Your 3/4 comma -68/5. Your 37/17 comma -68/5, your 13/5 comma -5/2, your 5 comma 0. So again, we know what this is going to do. This right here, this is going to shoot down like this. And so we know that this is going to come up like this. And this is going to shoot down like this. So we know that this is going to shoot up like this. Again, the multiplicity of each 0 associated with these vertical asymptotes was 1. That's an odd multiplicity. So if this goes down, this goes up. If this goes down, this goes up. We know that behavior. So really, we know that this right here, let me just kind of continue this in a different color. This is going to come right here, and it's going to approach the horizontal asymptote, again, the line y = 0, or the x-axis. You're going to have a hole right there, so you can just skip over that. So we're going to stay below the x-axis on that one. Again, we're approaching from below. We're not going to touch it. This one right here, again, this is going to come up like this. We're going to cross through that 5 comma 0. And what's going to happen is, let me go back. You see how it says local maximum point 8.464 comma 0.072? What that's telling you is that this guy is going to be increasing until you get to about right there. And then it's going to start coming back down and approaching that x-axis or the line y = 0. The main thing to understand about sketching this is just to know that this is coming down like this, and it's approaching the x-axis from above it, whereas on this side, it's approaching from below it. And that's because we crossed through right here at that 5 comma 0. So that's a very important feature of this graph, even if you don't have that local maximum point, something that you would do in curve sketching in Calculus 1. All right, then you have this local minimum point that you need here. Again, going back, it's going to be about 1.536 comma 13.928. And that's something I would just do from an estimation procedure. So let's just say you said it was about 1.5 or something like that. That would be close enough. So I'm just going to just say that it's going to look something like this. That part does not have to be perfect, especially at the pre-calculus level. And just coming to verify this with our computer generated graph, this is f of x is equal to, again, x minus 5 over the quantity x minus 1 times the quantity x minus 2 for x is not equal to -3. So just looking at this piece right here, we can see that it's going to shoot down like this. That tells me that this part's going to shoot up like that. And this right here is going to go and approach the x-axis or the line y = 0. You're going to have that hole there. Again, that's at -3 comma -2/5. So we're going to skip over that. And this is going to approach, but not touch the x-axis. And this piece right here, again, this is shooting down like this. And so this is going to shoot up like this. Then when you think about this, it's going to come up and cross through the x-axis. So we're going to be above the x-axis, and we're going to come up, and then we're going to start coming back down and approaching the x-axis from above it. But again, we're only going to touch it at that 5 comma 0 right there. And then just finishing things up, this right here, again, you'd have to have a turn. Just estimate it for now. That's going to be good enough. Just pick some place in there to turn. When you get to calculus, you can get the exact local minimum point. All right, for problem 10, we have f of x is equal to the quantity x plus 2 squared times the quantity x minus 1 over the quantity x minus 5 squared. So this guy is going to be simplified already. So what we want to do is move into finding the asymptotes. To find the vertical asymptotes, again, you want to take your denominator, set it equal to 0, and solve. So in this case, we have the quantity x minus 5 squared. For the denominator, we set that equal to 0, and we can solve this by just saying x minus 5 equals 0, add 5 to both sides of the equation, you get x equals 5. Now the important thing for sketching the graph is to realize that the 0 that's associated with this vertical asymptote is going to have an even multiplicity, right? So it has a multiplicity of 2. So let me just come down here and show this to you. So this is your x equals 5. That's your vertical asymptote. Now notice that if you look at this side of this guy's shooting up like this. If you look at the other side of this guy is shooting up like this. So that's our behavior because, again, on one side of this guy to the other side of this guy, you do not have a sign change. So that's what's creating this going up like this, and then this also going up like this. All right, now coming back, the next thing you would want to think about is, do we have a horizontal asymptote or do we have a slant asymptote? In this case, you're actually going to have a slant asymptote. How do I know that? Well, if you look at the degree of the numerator, it's going to end up being 3, and the degree of the denominator is going to end up being 2. So if the degree of the numerator is 1 more than the degree of the denominator, well, then you have a slant asymptote, and you will not have a horizontal asymptote. So let's come down, and we're going to do a little bit of simplifying so that we can do some polynomial long division. So we're going to simplify the numerator. So that was the quantity x plus 2 squared times the quantity x minus 1. So this is equal to, for this one right here, this is going to turn into this right here, just using your formula. So this becomes x squared plus 4x plus 4. So this quantity times the quantity x minus 1. So then from there, you're going to just take this, so this x, and multiply by the quantity x squared plus 4x plus 4. And then you have negative 1 times the quantity x squared plus 4x plus 4. If you want, you can go plus negative 1 like that to make it a little bit easier. And so essentially you're going to distribute the x to each guy inside the parentheses. So you have x cubed plus 4x squared plus 4x. And then you're going to distribute the negative 1 to each guy inside the parentheses. So just change the sign of each term. So negative x squared minus 4x minus 4. If you combine like terms, you're going to have x cubed. And then plus, you have this 4x squared minus x squared, that's 3x squared. And then plus, you have 4x minus 4x, that's 0. Those are going to cancel. And then you just have your minus 4. So the numerator is going to simplify to x cubed plus 3x squared minus 4. For the denominator, again, we just use our formula. So we have x minus 5 quantity squared. This is going to be equal to x squared minus 10x plus 25. So what we're going to do is set up our polynomial long division. So again, this is going to be your numerator. So x cubed plus 3x squared plus we have 0x here because we're missing x to the first power, and then minus 4. This is your denominator. So x squared minus 10x plus 25. We know how to do polynomial long division at this point, so I just went ahead and wrote this out. You can pause if you need to use this to check your work. But what you're going to end up with is x plus 13 for your quotient, and your remainder is 105x minus 329. All right, so coming here, we have f of x is equal to, again, x cubed plus 3x squared minus 4 over x squared minus 10x plus 25. This is equal to, this is your quotient, so x plus 13, plus your remainder is 105x minus 329, and we put that over the denominator, which is x squared minus 10x plus 25. So when we think about the slant asymptote, it's going to be this right here. So it's just the y is equal to x plus 13. The reason is because this part right here is going to go to 0 as x approaches positive infinity or negative infinity. So what happens is the graph of this guy is getting closer and closer to this y equals x plus 13. So let me come down here and show you this. So this guy in green, y equals x plus 13. So that's this guy right here. That's going to be your slant asymptote. All right, so to find the intercepts, we're going to take, for the x-intercepts, this guy right here, so this quantity x plus 2 squared times the quantity x minus 1 over the quantity x minus 5 squared. Set that equal to 0. Again, as we talked about many times, for this guy to be equal to 0, the numerator needs to be equal to 0, and the denominator needs to not be 0. So take your numerator, set it equal to 0, and solve. So you have x plus 2 quantity squared times the quantity x minus 1. This equals 0. So you take this x plus 2, set that equal to 0, subtract 2 away from each side, you get x equals negative 2. Then or, over here, you take this x minus 1, set that equal to 0, you add 1 to both sides, you get x equals 1. Now again, you have to pay attention to the multiplicity of each 0. This one is squared, so that means that this guy right here, this negative 2, so at negative 2 comma 0, we're going to touch the x-axis and turn around. But the multiplicity of this 0 is 1, so that's odd. So at 1 comma 0, we're going to cross through the x-axis. So this is our graph. Let me actually show you this on Desmos. I think it's too hard to see it there. It's actually kind of hard to see on Desmos too. Let me zoom way in. I gave you that link. So let's come down here. So what's happening is you're below the x-axis and you're coming to where you have negative 2 comma 0. So you're going to be on the x-axis, but you're just going to touch it and you're going to turn back around. Okay, so that's important there. And that's because the multiplicity of that 0 was 2, which is even. So there's no sign change on one side of this guy to the other side of this guy. That's what creates that behavior. So we're coming up. We're going to touch at negative 2 comma 0 and turn around. So we're coming down. And then at 1 comma 0, we're going to cross through the x-axis. Again, super important if you're trying to make at least a somewhat accurate graph. All right, now for the y-intercept, again, you just want to find f of 0. So this would be equal to the quantity 0 plus 2 squared times the quantity 0 minus 1 over the quantity 0 minus 5 squared. So this right here would be 2 squared, which is 4, times this would be negative 1. So 4 times negative 1 is negative 4. And this down here would be negative 5 squared, which is 25. So you'd have negative 4 over 25 as your result. So 0 comma negative 4 over 25 would be the y-intercept. All right, I'll just show you this again on Desmos because it's really hard to see on the graph that I gave you. Let me zoom way in. So this is 0 comma negative 0.16. And that's going to be this part right here, this negative 0.16. That's negative 4 over 25 as a decimal. All right, now we want to figure out, is our graph going to intersect the slant asymptote So remember the slant asymptote, that is y equals x plus 13. So I'm looking for the x comma y, or the point of intersection. So I'm going to take my function, x cubed plus 3x squared minus 4 over x squared minus 10x plus 25, and I'm going to set that equal to this guy over here, so this x plus 13. Well, the first thing I'm going to do to solve this is multiply both sides by the denominator, and that's going to give me x cubed plus 3x squared minus 4 is equal to the quantity x plus 13, so that's coming from here, times the quantity x squared minus 10x plus 25, so that's coming from here. All right, so just doing some simplifying of what's on the right, essentially you could take x times the quantity x squared minus 10x plus 25 and say plus 13 times the quantity x squared minus 10x plus 25. So you're going to distribute this into each guy. This would be x cubed minus 10x squared plus 25x, and then plus distribute this into each guy, 13x squared minus 130x plus 325. And then if you simplify, you're going to have x cubed, and then you have negative 10x squared, and then you have plus 13x squared. So that would give you plus 3x squared. You have 25x minus 130x. That's going to give you negative 105x. And then you have your plus 325. So this right here is going to be our right-hand side. So now we have x cubed plus 3x squared minus 4. So that was the left, is equal to, this came from what we just did. So the right is x cubed plus 3x squared minus 105x plus 325. All right, so if we look at this, we can subtract x cubed away from each side. So that's going to go away. We could subtract 3x squared away from each side. So that's going to go away. You would end up with negative 4 is equal to negative 105x plus 325. You can subtract 325 away from each side of the equation, and you get negative 329 is equal to negative 105x. And then, of course, you can divide both sides of the equation by negative 105. And you get x equals negative 329 over negative 105. So this right here would be equal to, you can of course cancel the negatives. So this would be a positive answer. This is 47 times 7. And this down here is 15 times 7. So let me cancel this with this. So this would be 47 over 15, or 3.13, where that 3 repeats forever. So coming down here, I have x equals 47 over 15. As a decimal, this is 3.13. And you put a little bar at the top here to show that that 3 repeats forever. If you find f of 47 over 15, you are going to get 242 over 15, and that's just me plugging in. And so this is your ordered pair, or your point of intersection. So 47 over 15, comma 242 over 15. Let me put a little border. I'm just going to say in decimal form, because this is how you're going to see it on Desmos. It's 3.13, again, where this repeats forever. And then comma, it would be 16.13, where this 3 repeats forever. Let me come back to Desmos and I'll just show you this. So this is the point of intersection. So this right here in green, this is our slant asymptote, and this is where the graph is going to intersect. So it's going to be that point right there. Again, it's going to be 47 over 15, comma 242 over 15 if you want the fraction version. But a lot of people like to work with decimals. So this guy is just approximating. So it's 3.1. It just does 3, but that 3 right there repeats forever, comma 16.1. Again, that 3 right there would repeat forever. So that's your point of intersection. All right, coming down here, again, I'm just going to organize my information. So the vertical asymptote, we know it's at x equals 5. Again, remember that the multiplicity associated with the 0 for this guy was 2, which is even. The slant asymptote is y equals x plus 13. The x-intercepts are negative 2 comma 0. The multiplicity of the 0 associated with this was 2, which is even. So there we're going to touch and turn around. And then 1 comma 0, the multiplicity of the 0 associated with this guy was 1. So that's odd. So we're going to cross through the x-axis there. The y-intercept is at 0 comma negative 4 over 25. And then again, you just take these x values. So from your x-intercepts, so negative 2 and 1, and then from your vertical asymptote, which is 5, and you use that to split the number line up into intervals. So anything less than negative 2, anything between negative 2 and 1, anything between 1 and 5, and then anything greater than 5. So if I look at this, I have in this interval negative 7 comma negative 1.38, where the 8 repeats forever. Then in this interval, negative 1 comma negative 0.05, where the 5 repeats forever. In this interval, 2.5 comma 4.86. In this interval, 10 comma 51.84. And then I have some additional points. So this is the one we talked about earlier. So that's where your point of intersection is. So 3.13, where the 3 repeats forever, comma 16.13, where the 3 repeats forever. Then we have this 8 comma 77.7, where that 7 repeats forever. And then we have 15 comma 40.46 and 21 comma 41.328. All right, this is a harder one to do because of all this. So you really have to mess with the scale. And that's why it's best for something like this, just to use Desmos, where you can zoom way in and see the features that you need. Just draw the graph as best as you can. You just need a rough sketch. But again, if you want to look at things on Desmos just to see what it looks like, again, you can just zoom out and then zoom in on the parts that you need. Just compare it to your graph. And again, you're just trying to make a rough sketch. You're not going to get this perfect. So everything's going to be in fraction form. Again, you could just use a calculator to put in decimal form or look at the Desmos link. It's already got that calculated for you. So this is 8, 700 over 9. This is 10, 1296 over 25. This is 21, 2645 over 64. This is 15, 2023 over 50. This is your 47 over 15, 242 over 15. Again, that's your point of intersection. This is your 5 halves, 243 over 50. Then when we get down here, this is where it gets really tight. So your -7, -25 over 18, your -2, 0. Again, that's your x-intercept where you're going to touch and turn around. Your 0, -4 over 25, that's your y-intercept. This is your 1, 0. Again, that's where you're going to cross through the x-axis. And so if you want to draw this, again, I'll look at the computer-generated version with you in a moment, but we already know that this right here is going to shoot up like that. And so this right here is going to turn like that. And it's going to come back like that and approach this y equals x plus 13. I know it's not going to touch over here because we found the point of intersection. That's going to be right there. So essentially, if I look at this piece, I know that this is going to shoot up like this. So just like that. And again, that goes back to the behavior. This is going to go up and this is going to go up because the multiplicity of the 0 associated with that vertical asymptote, x equals 5, was 2, which is even. So there's no sign change on one side of the sky to the other side of the sky. That's what's creating that. Then when we look at this part right here, we're going to, let me mark off this as a point of intersection. So we're going to come down like this, again, crossing through here, and we're going to be below the x-axis. We're going to have something like that where we touch and turn around, and we're going to stay below the x-axis, and then we're going to approach like that. This guy, and again, it only crosses there, so it's going to approach the line y equals x plus 13, but not touch it. So this one is a very hard one to draw. So let's just come down to the computer-generated version. It'll be a little bit better. So this is f of x equals the quantity x plus 2 squared times the quantity x minus 1 over the quantity x minus 5 squared. So again, I know that this goes up like that, and this is going to go up like that as well. This is going to come down, it's going to curve, and then it's going to approach that y equals x plus 13. This right here is going to come down, come down, come down, and we're going to cross through right there. So this is where we're going to intersect with that slant asymptote. So at 47 over 15, 242 over 15, and we're going to come down, come down, come down. This is where we're going to cross through the x-axis, so at 1, 0. So then we're going to come like this. We're going to go through our y-intercept, which is 0, -4 over 25. We're going to come right here to -2, 0. We're going to touch the x-axis, and then we're going to turn around. We'll go through that point right there. And then again, we're going to approach that y equals x plus 13, but not touch it. All right, let's take a look at the practice test. For the instructions, we're asked to solve each inequality. All right, for the first problem, we have the quantity -x minus 8 times the quantity 3x minus 4 times the quantity 2x minus 7 is greater than 0. So how do we solve something like this? So for this one, we know that we can replace the inequality symbol with equals and solve the resulting equation. So coming down here, we have the quantity -x minus 8 times the quantity 3x minus 4 times the quantity 2x minus 7. We set that equal to 0 and we solve. With this one, because this is in factored form, we can use the zero product property. So you just take each factor, so -x minus 8, set that equal to 0. Then or, this 3x minus 4, set that equal to 0. Then or, this 2x minus 7, set that equal to 0. So we're going to solve each one of these individually. So let's go -x minus 8 is equal to 0. Let's add 8 to both sides of the equation. Let's cancel this and say -x, or actually, let me write -1x so that's clear, is equal to, this would be 8 over here. We're going to divide both sides of the equation by -1. Let's go ahead and cancel this with this. And what we'll say is that x is equal to, let me fix this real quick. We have 8 over -1, that's going to be -8. Let me erase my scratch work here. And let's say that we have x is equal to -8. We're then going to put or. We're going to go with the next one. So we have 3x minus 4 is equal to 0. We're going to add 4 to both sides of the equation. This cancels. You get 3x is equal to 4. Divide both sides of the equation by 3. And so this would cancel. And you're going to get that x is equal to 4/3. Let me get rid of this. So let's put x is equal to 4/3. Then or. This one right here, you have 2x minus 7 is equal to 0. Let's add 7 to both sides of the equation. Let's cancel this. And let's go ahead and say that we have 2x is equal to 7. Divide both sides of the equation by 2. And we'll cancel this with this. And you're going to get x is equal to 7/2. So let me erase this and put x is equal to 7/2. So what's the purpose of doing this? Remember that if you take this guy right here and you set it equal to 0 and you solve, your real solutions correspond to x-intercepts on the graph. So in other words, you could take this right here and you could graph that. So you could say f of x is equal to the quantity -x minus 8 times the quantity 3x minus 4 times the quantity 2x minus 7. And you're going to see that you have an x-intercept that's at -8, 0. Then you're going to have one that's going to be at 4/3, 0. And then you're going to have one that's going to be at 7/2, 0. So let me say that this right here, these are going to be your x-intercepts. So all of these right here. I'm going to go to the graph real quick, and I've left you a link for these on Desmos, so you can just pause the video and click these if you want more detail. So this is your f of x equals the quantity negative x minus 8 times the quantity 3x minus 4 times the quantity 2x minus 7. So this guy right here. So notice you get those x-intercepts that we found. So negative 8, 0, 4/3, 0, and 7/2, 0. So why do we want the x-intercepts? What's the purpose of that? Again, these x values here, so the negative 8, the 4/3, and the 7/2, those are critical values. Those can be used to split the number line up into intervals where we can test. We know that the graph of a polynomial function is continuous. So what that means is that if I look at this interval right here for anything where the x value is less than negative 8, you can see that it's always above the x-axis. So the function values, or you could say the y values, are always going to be positive when x is less than negative 8. Then if you look at the x values between negative 8 and 4/3, it's always going to be negative in terms of the function values or the y values. If you look between x values of 4/3 and 7/2, the function values here are going to always be positive. And then if you look at anything where x is greater than 7/2, the function values are going to always be negative. So really all you have to do is find your x-intercepts, and then you can split the number line up into intervals, and then you can test in each interval. So you can either pick a number. So in other words, in this interval where x is less than negative 8, you could pick something like negative 9. You could plug it into the function, and you could see if it's positive or negative. Here, if we plugged in a negative 9, we would see that we get something that is positive. So you can conclude that in the interval where x is less than negative 8, this guy is going to be positive. And you can conclude, again, using the same process, where x is between negative 8 and 4/3, this guy's going to be negative. X is between 4/3 and 7/2, this guy's going to be positive, and then x is greater than 7/2, this guy's going to be negative. So once you have that information, you can come back up here and think about where this guy would be greater than 0. So I recommend putting your information into either a table or you can use a number line. So it's really up to you. With quadratic inequalities, I typically use a number line and I use a test value. So I pick something for x, I plug it in. Because polynomial inequalities get much more tedious, and it takes a lot longer to plug something in, I typically will use a table like this to organize the information. So again, these are the intervals we would set up. So this is where your x value is less than negative 8. This is between negative 8 and 4/3. This is between 4/3 and 7/2. And this is anything greater than 7/2. So this is just written in interval notation. You just take each factor and you think about, in each interval, would it be positive or negative? So this quantity negative x minus 8, this would be positive here where x is less than negative 8, and it would be negative anywhere else. And if this is confusing for you, you can pause the video and you can just say something like, well, where is negative x minus 8? Where is that greater than 0? And we can just add 8 to both sides of the inequality here. This would cancel. You get negative x is greater than 8. We would divide both sides by negative 1. Remember that if you divide both sides of an inequality by a negative, you have to flip the direction of the inequality symbol. So this becomes a less than now. And let's just go ahead and say that this negative 1 would cancel with this negative 1. So you get x is less than 8 over negative 1 is negative 8. So for any x value that's less than negative 8, this guy would be positive. So here, that's this category here. So this is positive. And you can do a similar thought process to figure out that in this interval, this interval, and this interval, this factor is going to be negative. Let me get rid of this. And I won't do that for each one because it would take a long time. But essentially for 3x minus 4, that factor, it's going to be negative here, and then positive here and here. And then for 2x minus 7, it's going to be negative here, and here, and then positive here. So then once you know this, you can put everything together. So the quantity negative x minus 8 times the quantity 3x minus 4 times the quantity 2x minus 7. Well, I would have a positive times a negative times a negative. So an even number of negative factors gives me a positive. We already saw from the graph that when x was less than negative 8, the function that we were graphing was positive. We were above the x-axis. Then in this interval right here, again, you'd have a negative, negative, and negative, 3 negatives, so this guy would be negative. Then in this interval right here, you have a negative, positive, negative, 2 negatives, so this guy would be positive. And then this guy is negative, positive, positive, so only 1 negative, so this would be negative. So this right here is what you would look at. Again, we want to know where it's greater than 0 or positive. So just coming back down here, I would just look at the intervals where that's going to be a positive. So that's right here, and then that's going to be right here. So in this guy, it would work. So that's where x is less than negative 8. Then I'm going to put the keyword or. This is another interval where it would work. So this is x is greater than 4/3 and less than 7/2. And let me come down here. I went ahead and did all this already just to save a little bit of time. So you have x is less than negative 8. or x is greater than 4/3 and less than 7/2. So this is your interval notation, and then this is graphing this guy. Now, if you follow with my videos, you know that I like to use a parenthesis or a bracket, depending on whether it's excluded or included. A parenthesis when it's excluded, a bracket when it's included. A lot of books use the open circle notation. That was just a little bit easier for the program that I was using to draw this. So feel free to put a parenthesis there where I've put an open circle and to put a bracket when I use a filled in circle. But this right here would be anything where we're less than -8, with -8 being excluded. Again, that's why there's an open circle. And this right here would be between 4/3 and 7/2, with both of those guys being excluded. Again, that's why there's an open circle here and here. Let me grab this and paste this in. Again, just verifying this with the graph. We're wanting to know where this guy right here, where is it greater than 0? So what are the x values for which the y values or the function values are greater than 0? So looking at this graphically, where am I above the x-axis? Well, it's going to be right here, again, where x is less than -8. And then it's going to be right here, again, where x is between 4/3 and 7/2. All right, what I'm going to do now is just rework problem 1 using a different approach. So this is something you can use if you want. I'm going to use this strategy for the rest of the practice test. Essentially, you're going to take your factors and just write them in the form of x minus k. Once you master this, it's going to be much, much quicker. It's going to be a little bit slow here because I have to stop and explain everything. But once we get going, it's going to be faster. So from the first factor here, I'm just going to pull out a -1. So let me write -1 here, and let me put this all the way over here. If I pull out a -1, just divide everything inside by -1. So -x divided by -1 is x. -8 divided by -1 is 8. Now I know this is not in the form of x minus k yet. You can change that over to x minus the -8 later on if you want. For right now, we're just going to write x plus 8. This right here, you're going to pull out a 3. So I'm going to put times 3. And so you're going to divide 3x by 3. That's x. And then minus divide 4 by 3. That is just 4/3. And then here you're going to pull out a 2. Let me put times 2. And so let me slide this down. Essentially 2x divided by 2 is x. And then minus 7 divided by 2 is 7/2. So this is greater than 0. If you simplify here, -1 times 3 times 2, that's -6. So let me just write -6 like this. Let me bring this over like that. Now, if you want to pause the video, I've given you a link for this. So we looked at it already. And I'll give you a link for this as well. So you can just look at that. And you can see that this graph and this graph are exactly the same. So I'm dealing with the same polynomial function at this point. What I'm going to do is make a modification though, and I'm not going to be dealing with the same polynomial function anymore, but it's not going to matter because I will have the same solution set. So I'm going to divide both sides of this inequality by -6. So this right here is going to cancel with this right here. So the left side will be the quantity x plus 8 times the quantity x minus 4/3 times the quantity x minus 7/2. Let me fix this. Now, before I deal with this side right here, let me show you this graphically so you can see that it's not the same. So I want you to look at the graph of f of x equals the quantity x plus 8 times the quantity x minus 4/3 times the quantity x minus 7/2. You have the same x-intercepts as what we looked at before. So -8, 0, 4/3, 0, and 7/2, 0. But something has happened here. If you look at the intervals where the function is positive and negative, they've been flipped. So if you looked at the original graph, when x was less than -8, well, this guy was positive. And then between -8 and 4/3, it was negative. Between 4/3 and 7/2, it was positive. And then for anything greater than 7/2, it was negative. Let me show you that again, just for the refresher. So this was the graph we were working with. So you can see that it's been changed. So coming back here, what do we need to do to get the same solution set? Remember that if you divide both sides of an inequality by a negative, you have to flip the direction of the inequality symbol. So we're going to flip here. So 0 divided by -6 is still 0, but this is now not going to be a greater than, it's going to be a less than. So now we're looking for where this is less than 0 or where we are below the x-axis. Again, coming to the graph, well now, since we're looking for where we're below the x-axis, it's the same solution. So x is less than -8 or x is between 4/3 and 7/2. So you can modify it like that and it makes it a little bit easier to find things. I know that I have a 0 that's going to be -8. I know that I'm going to have one at 4/3 and then 7/2. And again, you can even use this to set up a table in a similar way. So you have the factor of x plus 8. Again, you could write that as x minus a -8 if you want. You have x minus 4/3, x minus 7/2. So this would be your new table here. And you see you would have negative, negative, negative. So now this guy's negative. And then you have positive, negative, negative. So this guy's positive, 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 negative. So this guy's negative. And then positive, positive, positive. So this guy's positive. So if you're looking for where it's less than 0 now, you would be right here where x is less than -8. And then also right here So between 4/3 and 7/2. So it's the same solution. It's just that we've modified things. So we're looking at a different graph and a different polynomial. So we can still say that the solution, again, going from this, is x is less than -8, or x is greater than 4/3 and less than 7/2. All right, for problem 2, we have the quantity x minus 9 times the quantity x minus 3 times the quantity x minus 7 cubed is greater than 0. So again, I'm just going to write that x minus 9, that quantity times the quantity x minus 3 times the quantity x minus 7, this is cubed, this is equal to 0. So again, you can use the zero product property if you want. Take each one of these guys, set it equal to 0 and solve. Alternatively, this is already written for us as x minus k in each case. So you can just take this as a 0, this is a 0, and this is a 0. And really, we don't have to sit there and write out that x equals 9 or x equals 3 or x equals 7. We really just want the x-intercepts. So in other words, the x-intercepts here are going to correspond to those zeros. So you would have one, let me write at 3, 0, and then you'd have another one at 7, 0, and then another one at 9, 0. And I'm just writing this in the order of the number line. That's why it's a little bit mixed up. But this one is coming from this one is coming from this one, and then this one is coming from this one. I'm going to show you the graph real quick, just so this is clear. So here's your f of x equals the quantity x minus 9 times the quantity x minus 3 times the quantity x minus 7 cubed. So this guy right here. You have an x-intercept at 3, 0, one at 7, 0, and then one at 9, 0. So again, all you're doing here is setting up an interval where x is less than 3. You're looking between 3 and 7, between 7 and 9, and then anything greater than 9. So I'm just going to use a table. Again, if you want to pick something for x and plug it in and do it that way, that's up to you. But for this x minus 3 factor, again, it would be negative in this interval and then positive anywhere else. Then for this x minus 7 quantity cubed, it would be negative here and here, and then positive here and here. Then for x minus 9, it would be negative here, here, and here, and then positive here. So if we look at multiplying these guys together, again, you just look at, do I have an odd number of negatives or an even number of negatives? That's all you really need to know. So this is negative, 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 so this would be negative. This is positive, negative, negative, so this is positive. Positive, positive, negative, so this is negative, and then all positives, so this is positive. Now going back up, we wanted to know where it was greater than 0. So we're looking for where is it positive. So that's going to be right here and right here. So you see it's positive here and positive here. So let's write our solution as x is greater than 3 and less than 7. Or you could say x is greater than 9. All right, so coming down here, I already set up the interval notation and graphed it on the number line. So the x is greater than 3 and less than 7. That's going to be this part right here. So this is showing between 3 and 7 with both being excluded. And then we want the union with this part right here where x is greater than 9. So again, 9 is excluded here, so use a parenthesis, and you're going out to positive infinity. If you want to show this by graphing on the number line, again, I'm going to use an open circle at 3, and then 7, and then 9 to show those are excluded. Again, that's just easier for me with this program that I was using. If you want to use a parenthesis here, and then here, and then here, that's fine as well. You're just showing that it's excluded. So this is going to be between 3 and 7, again, with neither of those being included. And this is anything greater than 9. Again, 9 is going to be excluded. All right, coming down to the graph once again, we wanted to know where this guy right here, so let me just highlight it. So this guy right here, where is that greater than 0? So what are the x values for which the y values or the function values are greater than 0? So when I look at the graph, I'm looking for where it's above the x-axis. So that's going to be right here. So between 3 and 7 in terms of the x values. And then also that's going to happen right here where x is greater than 9. So let me just write out the solution one more time. Again, this is showing that it's for x is strictly greater than 3 and less than 7, or it would be for any x value where we're greater than 9. All right, for problem 3, we have the quantity x minus 1 times the quantity x plus 1 cubed is less than or equal to 0. So let me just write x minus 1, this quantity, times the quantity x plus 1. You could write x minus a negative 1 if you want. This is going to be quantity cubed, and I'm just going to set this equal to 0. Again, you know that you would have a 0 of 1 and then negative 1. But you don't have to write x equals 1 or negative 1, because again, we're just trying to figure out what are the x-intercepts. So what are the x-intercepts? So here you would have one at 1, 0, and then negative 1, 0. So negative 1, 0, let me write that one first, and then also at 1, 0. And the graph f of x equals the quantity x minus 1 times the quantity x plus 1 cubed. So it's going to be this guy right here. And you can see you do have an x-intercept at negative 1, 0, and that's coming from this guy right here. And then you have one at 1, 0, that's coming from this guy right here. Let me go back up. So all you really need to do is split the number line up into intervals. So one would be where you're less than negative 1, one would be between negative 1 and 1, and then one would be anywhere greater than 1. So if we look at this factor x plus 1 quantity cubed, it would be negative in this interval, and then positive in this one and this one. Then the factor x minus 1, that would be negative here and here, and then positive here. And then when you multiply those guys together, so this quantity x plus 1 cubed times the quantity x minus 1, again, you're looking at this is negative and this is negative. Negative times negative is positive. Then this is a positive and this is a negative, so that would give me a negative. And this is positive and positive, so this is a positive. So if we're looking for where this guy is less than or equal to 0, then what we want is this interval right here, but you want to include the endpoints because we have the less than or equal to. So we'll say that x is greater than or equal to -1 and less than or equal to 1. Again, I already have the interval notation set up for us. So from -1 to 1, again, you have a bracket with each right there because they're both included because we had a non-strict inequality. If you look at this on the number line, again, from -1 to 1, you can put a filled in circle here. So that's to include those numbers. You can also put a bracket here and a bracket here. Again, that's going to be personal preference. Normally I use the bracket, but again, the program that I'm using, this was just a little bit easier to do. So just verifying this, again, using our graph, we want to know where this guy is less than or equal to 0. So where is it 0? Well, that would be if we're on the x-axis, so that point and that point. And then where is it less than 0? Where are we below the x-axis? So that's going to be this right here. So anything from -1 to 1 with both being included, that's where we're going to satisfy our inequality. All right, let's take a look at problem 4. So we have the quantity 3x minus 2 times the quantity -3x plus 2 times the quantity x minus 3 squared is greater than 0. Okay, so there's multiple ways to look at this. I'm going to tell you in advance that the answer here is no solution. One way you can do this is by factoring, and there's multiple ways to factor and see this, but I'll show you 2 different ways on that. Another way, again, we can always use the zero product property. For this one, I think it's a little bit complicated, so maybe I'll just do it both ways so that it's crystal clear for you. Let me use the zero product property first. So let's say we take 3x minus 2, so this is a quantity, times the quantity -3x plus 2, and then this quantity here, we're going to multiply by x minus 3. And this is a quantity squared here. And all we're going to do is set this equal to 0. Again, this would give us the x-intercepts. So if I look at this one and this one, you're going to see that you have the exact same solution. So in other words, if you set 3x minus 2 equal to 0, let's go or -3x plus 2 is equal to 0. For this one, we'll just go or. You could just work with x minus 3. We'll set that equal to 0. We know it's a double root. So this you would just add 2 to both sides of the equation. This would cancel. You get 3x is equal to 2. Divide both sides by 3, and so this would cancel. So you get x is equal to 2/3. So that's going to be for this one. So that gives me an x-intercept that is 2/3, 0. Now this one right here, I'm going to get the same x equals 2/3. So in other words, I'm going to end up with a double root. I'll show you how to factor that in a moment and make that obvious. But I'm just going to subtract 2 away from each side of the equation. This cancels. You're going to have -3x is equal to -2. We're going to divide both sides of the equation by -3. So this is going to cancel. So you get x is equal to -2 over -3. Well, that's positive 2/3. So this over here would be x is equal to 2/3. So again, you have a double root. So when you look at that x-intercept that's at 2/3, 0, what's going to happen is because the 0 is of even multiplicity, it's going to touch and turn around. The same thing is going to be true here. Let me add 3 to both sides. So this cancels. You get x is equal to 3. And for this one, it's obvious because the exponent here is a 2. So we know the 0 is of multiplicity 2, and that's an even multiplicity. So at 3, 0, it's going to touch and turn around. Let me put this into an easier format to understand. I'm just going to erase this. You can write that down for your notes if you want. But what I'm going to do is just factor out a -3 from here and a 3 from here. Or if you want, you could just factor out a -1 from here. Let me just start with that. I'm going to have -1 here. Don't touch this one, so we'll have 3x minus 2. And then this one, you're pulling out the -1. That's how I got it out here. So inside, you're just going to divide everything by -1. So -3x divided by -1, that's positive 3x. Positive 2 divided by -1 is -2. And then this right here would be the quantity x minus 3. This would be squared. And you could set this equal to 0. And again, you can combine these two, the quantity 3x minus 2 times the quantity 3x minus 2. You could just say that's the quantity 3x minus 2 squared. Let me move this down here and put this like this. So if you look at it this way, now you can tell that that x equals 2/3 is a double root, and x equals 3, you knew that was a double root already. Again, because you had the exponent of 2 and the exponent of 2. Now let me change this over into our inequality here, so this is a greater than. Is this ever going to be true? No. And the reason is because when you look at this part right here, this is a quantity squared, and this is a quantity squared. So if I have this guy, it would be either 0 if x is 2/3 or positive anywhere else. This would be 0 if x is 3 or positive anywhere else. So a positive times a positive will give me a positive, and 0 times a positive will give me 0. So the product here of these two will either be 0 or some positive number. So I'm then multiplying that by -1. So if it's 0, it stays 0. 0 is not greater than 0. If it's positive, it's going to be flipped to negative, and a negative is never greater than 0. So just by looking at this, I can immediately say that it's not possible to have a solution. We would say that there's no solution for this problem. Now I'm going to show you the graph. So this is f of x equals the negative of the quantity 3x minus 2 squared times the quantity x minus 3 squared. And again, this x-intercept here, which is 2/3 comma 0, this is coming from this guy right here. Again, you have an exponent of 2, so that 0 has an even multiplicity, so we're going to touch and turn around at that x-intercept. Same thing here. So the 0 is 3, so the x-intercept is 3 comma 0. The exponent here is 2, so again, it's an even multiplicity, so we're going to touch and turn around. So we're never going to cross over the x-axis. We're going to either be on the x-axis when x is 2/3 or x is 3, so that gives us a y value of 0, or we're going to be below that where the y values are negative. So it's not possible for this guy to ever be positive. So again, there's no solution. Now, we already know the answer. Let me show you one other way you can do this, just to get some practice with this. Remember that you can write things in the form of x minus k. I recommend you do that because it makes things simpler. But what happens is in some cases, you're dealing with a negative, and you have to remember that if you multiply or divide both sides of an inequality by a negative, you've got to flip the direction of the inequality symbol. So I'm just going to do this to show you what could go wrong in case you're doing this. So from this one, you could pull out a 3. So let me pull out a 3. So this would be x minus 2/3. And then from this one, you could pull out a negative 3. So 3 times negative 3 is negative 9. And then inside, you're dividing everything by negative 3. So this would be x minus 2/3. And again, you can just combine those and just say this is x minus 2/3 quantity squared. This is your same x minus 3 quantity squared. And again, you're looking for where this is greater than 0. We can divide both sides of the inequality by negative 9, just to make the problem simpler. But when you do that, again, it's a very common mistake to forget this. You have to now flip the direction of the inequality symbol. So this will cancel away. Again, if I graph this now, it's not going to be the same, so keep that in mind. But if I flip this, I would have the same solution set. So this is the quantity x minus 2/3 squared times the quantity x minus 3 squared. And we want to see where that is less than 0. Now, could this ever be less than 0? No, because this is a quantity squared, and this is a quantity squared, so this is 0 or positive. This is 0 or positive, so the product here will be 0 or positive. It will never be less than 0, or you could say it will never be negative. So once again, there's no solution. Let me come down, and I'll just show you this. I've graphed this one as well. Again, the function looks different, but we can get the same solution set from it as long as we modified that inequality. So here, f of x is equal to the quantity x minus 2/3 squared times the quantity x minus 3 squared. You'll have a link for this one as well. You've got the same x-intercept of 2/3 comma 0, and then 3 comma 0, but now we're going to look for where it's below the x-axis or negative, and that's never going to happen. Again, because this x-intercept is involved with an even multiplicity. That 0 was 2/3 with a multiplicity of 2. It's going to touch and turn around. This one is 3 with a multiplicity of 2, so it's going to touch and turn around. So from the graph, again, you can easily see that this guy will never be negative. So once again, you can just conclude that there's no solution. All right, let's take a look at problem 5. This is one where I think you can greatly benefit from changing things into the form of x minus k immediately. So what you can do is just pull everything out. So I have 1 over 100. From this, I would pull out a 2, so I'm just going to multiply by 2. From this, I would pull out a 3. From this, I don't have to pull out anything, and then from this, I would pull out a negative 1. So inside, again, you're just going to make everything in the form of x minus k, so you can divide everything here by 2. So 2x divided by 2 is x, and then plus 5 divided by 2 is 5/2. Now you could write that as x minus a negative 5/2 if you want. I'm just going to leave it like that. Here you divide everything by 3. So this would be x minus 8/3. Here you just leave it. So this is x minus 5. Here everything's going to get divided by negative 1. So this is x plus 9. Again, if you want, you could write that as x minus a negative 9. Let me clean this up. So with 102, there's a common factor of 2. So 100 divided by 2 is 50. And you can just get rid of this. So basically you would have negative 3 over 50. So let me just write that like that. I'm just going to slide these down like that. And this would be greater than or equal to 0. Actually, I need to slide this so I can fit this. Put this in the middle. I'm going to multiply this by negative 50 over 3. And that probably should be like that. And this is times negative 50 over 3. So this right here is going to cancel and just give me 1. So the left side is the quantity x plus 5/2. Times the quantity x minus 8/3 times the quantity x minus 5 times the quantity x plus 9. Now, this over here is still going to be 0, but you need to remember, if this is negative here, you have to flip the direction of this inequality symbol. So let me write flip, just so that's crystal clear. So instead of a greater than or equal to, this is going to be a less than or equal to, and this would just be 0. 0 times anything is going to be 0. Again, you can replace this with equals. And this over here again would be x plus 5 halves. Let me fix that. Then times x minus 8 thirds. Then times x minus 5. Then times x plus 9. So all I want, again, are the x-intercepts. Let me write out x-intercepts here. From this one, it would be negative 9, 0, because the 0 there is negative 9. And then you would have one at negative 5 halves, 0. Again, the 0 there would be negative 5 halves. And then you would have one at 8 thirds. So 8 thirds, 0. And then you would have one at, let me slide this over, your 5, 0. So these are your x-intercepts. Again, you're just going to use that to break the number line up into intervals. So this is our f of x equals the quantity x plus 5 halves times the quantity x minus 8 thirds times the quantity x minus 5 times the quantity x plus 9. This is your x-intercept that's negative 9, 0, your x-intercept that's negative 5 halves, 0, your x-intercept that's 8 thirds, 0, and then the final one, your x-intercept that's 5, 0. So you have an interval where you're less than negative 9, between negative 9 and negative 5 halves, between negative 5 halves and 8 thirds, between 8 thirds and 5, and then anything greater than 5. So setting up a table, again, there's your intervals, anything less than negative 9, between negative 9 and negative 5 halves, between negative 5 halves and 8 thirds, between 8 thirds and 5, and then anything greater than 5. So I have this factor x plus 9. So it's going to be negative here and then positive everywhere else. I have a factor x plus 5 halves, negative here and here, positive everywhere else. I have a factor x minus 8 thirds, negative here, here, and here, positive everywhere else. And then I have a factor x minus 5, negative here, 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 and here, and then positive here. So again, when I multiply these guys together, I just look at negative, 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 negative. So I have 4 negatives. That's an even number. So this is going to be positive. Then here is positive, negative, 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 3 negatives. So this is negative. Positive, positive, negative, negative, 2 negatives. So this is positive. And then positive, 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 negative. So 1 negative. So this is negative. And then all positives. So this is positive. Now, if I go back, remember this is less than or equal to 0 that we're looking for. So you'd be negative here and then also here. So let me highlight those. I know it doesn't show up very well, but you would say that x is greater than or equal to, because this is a non-strict inequality, negative 9, and less than or equal to, this would be negative 5 halves. Then you want to use or, you want this one right here. Again, you want to include these guys because it's a non-strict inequality. So you would say that x is greater than or equal to 8 thirds and less than or equal to 5. And again, I've already written this in interval notation. So you want between negative 9 and negative 5 halves. They're both included, so I have a bracket next to each. And then the union with, you want between 8 thirds and 5. And again, both of these are included, so we have a bracket next to each. Then we have our number line, again, between negative 9 and negative 5 halves. We used a filled in circle here just to show they're included. If you want to use a bracket, that's fine as well. And then here we have between 8 thirds and 5. Again, a filled in circle is used with each to show that it's included. You can use a bracket for each one there as well. So again, just confirming this with the graph, if you look at this, where's this guy going to be below the x-axis? Well, you can see that it's between negative 9 and negative 5 halves. So right there. Now, because it's a non-strict inequality and we have the or equal to 0 part, negative 9 would be part of the solution and negative 5 halves. That would also be part of the solution. So this right there, that would be the x is greater than or equal to negative 9 and less than or equal to the negative 5 halves. Then you have this piece right here, where we're also going to be below the x-axis. And then right here at 8 thirds and then 5, those would have to be included because we have the or equal to 0 part. So we would say, or we have x is greater than or equal to 8 thirds and less than or equal to 5. Okay, so just in case you want to see it, this is the original function. So we had f of x equals 1 over 100 times the quantity 2x plus 5 times the quantity 3x minus 8 times the quantity x minus 5 times the quantity negative x minus 9. We were looking for where this guy right here was greater than or equal to 0. Remember, we flipped because we divided both sides by a negative, so the direction of the inequality symbol got flipped. So here, if you look at the graph, you'd have the same solution set. So now we're looking for where this guy is 0 or greater than 0, so meaning we're on the x-axis, so right there and right there, so at negative 9 and at negative 5 halves, and then above the x-axis where we're positive, so right there. And then this part right here, again, we're on the x-axis at 8 thirds and then also 5, and then we're above that right there. So just looking at this graph, again, you get the same solution. You would say x is greater than or equal to negative 9 and less than or equal to negative 5 halves, or x is greater than or equal to 8 thirds and less than or equal to 5. All right, let's take a look at problem 6. So we have negative 1 over 30 times the quantity 2x minus 7 times the quantity 3x minus 1 squared times the quantity x plus 3 squared is less than 0. Okay, so we have negative 1 over 30. I'm going to pull out a 2 from this. So times 2, and I'm going to end up pulling stuff out from this one as well. So let me put some space here. So here I would just say this is x minus 7 halves. Again, I pulled out a 2, so I'm just dividing this by 2 and this by 2. Then for this one again, because this is squared, you have to be careful. When you want to pull out the 3 there, you're going to do 3 and then times the quantity x minus 1 third like that. And so this would be squared like this. So 3 squared is actually going to be 9. So that's what you're pulling out. So this is times 9 like that. And so you would have this quantity x minus 1 third squared. And then this is times the quantity x. You can go minus the negative 3 if you want. I'm just going to write x plus 3 quantity squared. And this is less than 0. This right here, if you look at 2 and 30, there's a common factor of 2. So cancel this with this. This would be 15. And then between 15 and 9, there's a common factor of 3. So cancel this with this. This would be 5, and this would be 3. So you'd end up with negative 3/5 over here. So this is negative 3/5. And I'm just going to multiply this by negative 5/3 over here. Let me scooch this down. So I'm going to go times negative 5/3 over here. So this would cancel and just give me a 1. So on the left, I have the quantity x minus 7 halves times the quantity x minus 1 third squared times the quantity x plus 3 squared. And instead of this being a less than, again, because I multiplied both sides by a negative there, you've got to flip the direction of the inequality symbol. So we're going to flip. So this isn't a less than, this is a greater than. So 0 times anything is 0, so this is still 0 over here. Now, again, you can replace this with equals, and then you can just say, well, what are my x-intercepts going to be? What are the zeros? The zeros correspond to x-intercepts as long as they're real zeros. So this is the quantity x minus 7 halves times the quantity x minus 1 third squared times the quantity x plus 3 squared is equal to 0. So you would have x-intercepts. Let me write this out. And let me see if I can go in order. So this one would be at negative 3 comma 0. And then the next one, you would have 1/3 comma 0. And then the next one would be 7 halves comma 0. Again, let's look at the graph real quick and verify this. All right, so coming down here, this is your f of x equals the quantity x minus 7 halves times the quantity x minus 1/3 squared times the quantity x plus 3 squared. You see you have your x-intercept here at negative 3 comma 0, here at 1/3 comma 0, and here at 7 halves comma 0. Notice that the 0 here was negative 3. It's got an even multiplicity because it's squared, and it touches and turns around. Same thing with this one. The 0 is 1/3, so you have that 1/3 comma 0. And so because this is squared here, this is going to touch and turn around. It will not cross through. This one crosses through because you have an odd multiplicity there for that 0. The multiplicity is just 1. Let me come back up. So again, you just use this to set up your intervals on the number line. So anything less than negative 3, anything between negative 3 and 1/3, anything between 1/3 and 7 halves, and anything greater than 7 halves. So you have this factor right here, x plus 3 quantity squared. We know that it's going to be 0 when x is negative 3, and then positive everywhere else. So in all these intervals, it's going to be positive. For x minus 1/3 quantity squared, again, in all these intervals, it's going to be positive. It's only going to be 0 when x is 1/3. Everywhere else it's positive, it's never going to be negative. And then this x minus 7 halves here, that's going to be positive when x is greater than 7 halves. So in this interval right here, it would be negative everywhere else. So because in this one, and this one, you have a positive times a negative, in each case, you're going to end up with a negative. So this is negative, 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 and then it's only going to be positive right here. So if we look at our inequality, again, it's a greater than that we're looking for. So where's this guy greater than 0? Well, it's only going to be right here. So you would say that x is greater than 7 halves. That's the only place where this guy is going to be positive. So that interval right there. So coming down here, let me just rewrite this. So you could say that x is greater than 7 halves. So this is your interval notation. So anything greater than 7 halves. And then graphically, this is 7 halves. That's 3.5. Again, you can use an open circle like I did here. You can use a parenthesis if you want, and then just shade everything to the right. Again, coming back to the graph, if we look for where this guy right here is greater than 0. So where are we above the x-axis? Again, this is negative, negative, negative. It's going to go to 0, but it's touching and turning around. Negative, negative, negative. It's going to go to 0, but again, it's touching and turning around. So it never makes it to positive until we cross through this guy right here. So this right here is what you're looking for the solution. You want to say it's where x is greater than 7 halves. Again, if you want to do this in terms of the original problem, you can look at that graph as well. So this is for f of x equals negative 1/30 times the quantity 2x minus 7 times the quantity 3x minus 1 squared times the quantity x plus 3 squared. You're going to be looking here. Remember, we flipped the direction of the inequality symbol. You're looking here for where this guy is less than 0. So that's going to be this right here. Again, it's the same solution. We modified the function, so of course we're going to modify the graph, and so we're looking for something different here, but it's the same solution. Here it's just x is greater than 7 halves if you're looking for where this guy right here is less than 0. All right, for problem 7, we have the quantity x plus 8 squared times the quantity x plus 6 squared times the quantity 3x plus 11 is greater than or equal to 0. Okay, so looking at this, let's just first pull out a 3 from this. So I'll put the 3 out in front. This is x plus 8 quantity squared, and then times x plus 6 quantity squared. I pulled out a 3 from here, so just divide everything inside by 3. So 3x divided by 3 is x, and then plus 11 divided by 3, that's just 11 thirds. So this would be greater than or equal to 0. So if I graph this, or if I graph this, those are going to be the same. But what I'm going to do is modify this, just to make it simpler. I'm going to divide both sides of the inequality by 3. And so that is going to change the polynomial function that we're working with. So this would cancel with this. Let me slide down a little bit. And so what you're going to end up with is this quantity x plus 8 squared times the quantity x plus 6 squared times the quantity x plus 11 thirds is greater than or equal to 0, because 0 over 3 is 0. So let me get rid of this. Now, again, when you look at the graph of this and the graph of this, they will be different. But if you compare this problem to this problem, they will have the same solution set. So in terms of the x-intercepts here, we're just going to say this is equal to 0. So we have the quantity x plus 8 squared times the quantity x plus 6 squared times the quantity x plus 11 thirds. Your x-intercepts would be, you would have one at -8, so -8 comma 0. Notice that the multiplicity of that 0 is 2, so it's even, so that means it's going to touch and turn around there. You'd have another one at -6 comma 0. Again, the multiplicity of that 0 is 2. That's even, so it's going to touch and turn around there. And then this one, it would be -11 thirds comma 0. The multiplicity of that 0 is going to be 1, so here it's going to cross straight through. So this is your f of x equals the quantity x plus 8 squared times the quantity x plus 6 squared times the quantity 3x plus 11. So this is what we had before we pulled the 3 out. And if you notice, you have the x-intercept of -8 comma 0, the x-intercept of -6 comma 0, and the x-intercept of -11 thirds comma 0. So where is this guy greater than or equal to 0? Well, it's going to be 0 here, and then here, and then here, and then it's going to be greater than 0 here. And we'll see this, we'll put the answer together formally in a little while, but for right now, just think about how we can do that. The interval notation on that is a little bit tricky. So let's go down, and I'll show you the other graph. Again, the graph is different because this function that we're working with is now different, it's been changed, but the solution is still going to be the same. So we have f of x equals the quantity x plus 8 squared times the quantity x plus 6 squared times the quantity x plus 11 thirds. So where is this greater than or equal to 0? Well, again, it's going to be 0 here, and then here, and then here, and then it's going to be greater than 0 right here. So basically you would have an answer where x is equal to -8, or x is equal to -6, or x is greater than or equal to -11 thirds. So just going through and using a table, this is your interval that is less than -8. This is between -8 and -6. This is between -6 and -11 thirds. And this is greater than -11 thirds. So this x plus 8 quantity squared and this x plus 6 quantity squared, again, those are always going to be non-negative. They're either 0 or positive, and in the intervals we have here, they're always positive. So these are always positive. When you come to this x plus 11 thirds here, well, that's going to be negative in all these intervals until you get to this interval right here, where you're greater than -11 thirds. So if you look at that, that's going to create positive, positive, negative. We're going to have a negative, you have the same thing here, negative, same thing here, negative, and then finally here, it's going to be positive. So if we're looking for the part where it's greater than 0 or positive, that's going to be right here. The tricky thing is here is that you have the greater than or equal to, so you really have to think about, well, what were the x-intercepts? That's where the function value is 0, so the x values there would also work. So you would say that x is equal to -8, then you could put or, x is equal to -6, then or, x would be greater than or equal to this -11 thirds. So that one's a little bit tricky to answer. All right, let's look at the interval notation now. So for x equals -8, for that part, this is the notation right here. If you're doing it in interval notation, so you're going to have a bracket, then you're going to have the number. So in this case, it's -8, and then comma, you'll put the same number, so -8 again, and then close this off with a bracket. So that's how you would show x equals -8. Then you have the union with, you have this x equals -6. So the same strategy here, you have a bracket, -6, comma, -6, and then a bracket. So that's how you show the -6 part. And then the union with, this part right here is very straightforward. We're working with x is greater than or equal to -11 thirds. So you want a bracket here to show that -11 thirds is included. And then you have your comma, this is going out to positive infinity. Okay, so graphing this interval on the number line, that's pretty straightforward. You know that a filled in circle is going to include the number. So we're just going to put a filled in circle at -8. So this is included. A filled in circle at -6. So this is included. A filled in circle at -11/3. So that's going to be included. And then you're going to shade everything to the right of -11/3 to finish this guy off. Again, we already looked at the graph. Let me erase this and I'll just do it again. We're looking for where the values for the function are going to be 0. So that's right here and right here and right here. So that's at your x-intercepts. X value of -8, X value of -6, and an X value of -11/3. Then you're looking for also where it's greater than 0. So that's going to be this part right here where the X value is greater than -11/3. So once again, I'll just put this all together and say X could be equal to -8 because at -8, the function value is 0. Then or X could be equal to -6 because again, the function value would be 0 there as well. And then or you could have X being equal to -11/3 because again, the function value is 0 there, or anything greater than that. So X is greater than or equal to -11/3. So that one's a little bit tricky. All right, for problem 8, we are going to have the quantity 2x minus 9 times the quantity x minus 4 squared times the quantity 5x squared plus 3x plus 20 is less than 0. Okay, for this problem, the first thing that I notice is that I could pull out the 2 from here. Again, you don't have to, but it's what I like to do. So let's just pull that out. Inside, you'd have x minus 9 halves. And then this would be x minus 4 quantity squared. This one is a little bit tricky. We did a problem that was similar to this in the lesson. Let me just copy it. So 5x squared plus 3x plus 20. And let's say right now that this is less than 0. I'm going to deal with this in a moment. So let's divide both sides of the inequality by 2. And this would cancel over here with this. And this over here, 0 divided by 2 is just 0. So you can just erase this, and this problem right here and this problem right here, they'll have the exact same solution set. Again, if you graph this and if you graph this, they'll be different, but if you look at the solution graphically, it'll be the same. For right now, let's just think about the x-intercepts. So if I replace this with equals, and I say that we have x minus 9 halves, that quantity times quantity x minus 4 squared, times quantity 5x squared plus 3x plus 20, well, let me fix this. I know I have an x-intercept that's going to be 9 halves comma 0, and another one that's going to be 4 comma 0. Let me put these in order. So 4 comma 0. The multiplicity here for this 0 is 2. So I know at that 4 comma 0, it's going to touch and turn around. So these are the x-intercepts here. The other one is going to be, again, 9 halves comma 0. Now, what about this one right here, this 5x squared plus 3x plus 20? Let's look at the graph real quick. So this is the graph of f of x equals 5x squared plus 3x plus 20. You will notice that this guy does not have any x-intercepts. Why is that the case? Why doesn't this cross the x-axis? It's because if you set this equal to 0 and you solve, you're going to get 2 non-real complex solutions. So if you're looking at something like that and you want to tell without going through the whole thing, you can just work with the discriminant. Remember that if you have x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a, this is the quadratic formula. So this part right here is called the discriminant. If that is negative, it tells you have 2 non-real complex solutions. So that's all you have to figure out here. You don't need to do the whole thing. You could just say, well, what is b squared minus 4ac? Well, a is 5, b is 3, and c is 20. Let me actually move this down a little bit. So b squared, 3 squared would be 9, minus 4 times a is 5, times c is 20. So you would do 9 minus 4 times 5 is 20, 20 times 20 is 400. And 9 minus 400 is negative 391. So this is negative. Again, we can see that clearly. We're not going to have any x-intercepts as proven by this. We would have 2 non-real complex solutions. So there's no real number that we can plug in for x here to where we would get a y value of 0. So that's what's creating that. So let's come back up and just say we would go with these x-intercepts right here. Let me just show you this on both of these. So this is the original function. If you want to work with that, you have f of x equals the quantity 2x minus 9 times the quantity x minus 4 squared times the quantity 5x squared plus 3x plus 20. So this guy right here. And you'll see that you have an x-intercept at 4 comma 0. Again, it's going to touch and turn around there because the multiplicity is 2. It's even. Then you have an x-intercept at 9 halves comma 0. Again, that's coming from this. If you do 2x minus 9, set that equal to 0 and solve, you're going to get 9 halves as the solution. So you have this one right here. The multiplicity of that 0 is 1, so it's going to go straight through. Now, if I look at the other version, again, this is where we modified it. You're going to have the same solution that you get from it. The graph is different because you have a different function. So this is f of x equals the quantity x minus 9 halves times the quantity x minus 4 squared times the quantity 5x squared plus 3x plus 20. Well, you still have that x-intercept of 4 comma 0 and an x-intercept of 9 halves comma 0, but the graph is going to be different. But we'll have the same intervals of where it's negative and where it's positive and things like that. So we're going to have the same solution set. Let's go back up and let's just put the information together in a little table. So you can have an interval where we're less than 4. You can have an interval between 4 and 9 halves, and then an interval that's greater than 9 halves. So this x minus 4 quantity squared, again, it's going to be positive in all these intervals. X minus 9 halves would be negative here and here, and then positive here. So where we're greater than 9 halves. This was a little bit tricky if you've never seen this before. You have 5x squared plus 3x plus 20. I have here positive, positive, positive. Why is that the case? It's because no matter what real number we plug in for x, it's always going to be positive. Again, if we come back to the graph of this guy, just to look at this, again, we have the f of x equals 5x squared plus 3x plus 20. If you don't have any real zeros for this guy, well, you're either going to always be above the x-axis, so the function values are always positive, or you'll always be below the x-axis, so the function values will always be negative. For this, you could just pick something, so f of 0. You'd have a 0 there and a 0 there, so this would just be 20. So if this is positive, something like this is always positive. If it's negative, then it's always negative. So that's all you have to keep in mind. Let's go back down. So positive, positive, positive there. And again, to put these all together, when we find our product, you have a positive, negative, positive, so that's negative. Positive, negative, positive, so that's negative. Positive, 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 so that's positive. We're actually looking specifically where it's less than 0, so it's a strict inequality. So you would say that it's where x is strictly less than 4, or where x is greater than 4 and less than 9/2. So the 4 and 9/2 have to be excluded there. So coming down here, again, I've already got this written for us. So you have x is less than 4, or x is greater than 4 and less than 9/2. So that's going to be your interval notation for that. Just make sure you're using a parenthesis there for each guy, because none of those are going to be included. And then graphically, if you want to use a parenthesis here at 4, and then here at 9/2, which is 4.5 in decimal form, that's fine. Again, I just used the open circle because it was easier here. So basically, you're going to be less than 9/2. You just have to exclude 9/2 itself and 4. So those are all the values that are going to work. Again, coming back to the graph, and you can use this one or the other one, it's not going to matter. If you look at where the function values are less than 0, well, it's going to be this piece right here and this piece right here. You just have to make sure you're excluding this right here, the 9/2 value for x, and this right here, the 4 value for x, because at those values, you're going to have a function value that's 0, and we want it strictly less than 0. So you want this piece of the graph right here, where x is less than 4, and then you could say, or this piece of the graph right here, where x is greater than 4 and less than 9/2. All right, for problem 9, we have the quantity x plus 4 times the quantity x minus 1 times the quantity negative 2x squared minus 5x minus 9 is less than or equal to 0. So just like in the last problem, we have this guy right here. So this negative 2x squared minus 5x minus 9. Again, I would check the discriminant on that. So what is b squared minus 4ac? Well, here your a is going to be negative 2, your b is going to be negative 5, and your c is going to be negative 9. So what is b squared? Well, b is negative 5. Let me actually just write all this out so nobody is lost. So this would be negative 5, and you want to wrap that. That's going to be squared. Then minus 4 times a is negative 2, and then times c is negative 9. So this would be what? Negative 5 squared is 25. And then this, I know it would be negative because you have negative, negative, negative. So 4 times 2 is 8. 8 times 9 is 72. So 25 minus 72, that's going to be negative 47. So again, I only care about the fact that it's negative. Because it's negative, it tells me that I have 2 non-real complex zeros for that guy. So I don't have to worry about it. I don't have to try to find x-intercepts because there won't be. If I go and look at the graph of this guy, this is f of x equals negative 2x squared minus 5x minus 9. You can see this guy is always below the x-axis. So it's always going to be negative in terms of its function value. Again, you can always just say something like, what is f of 0? This would go away and this would go away, so you just get negative 9. And so we know it's going to be negative for all real numbers. So coming back up, I could do x plus 4, and then times x minus 1, and then times negative 2x squared minus 5x minus 9. We'd set that equal to 0. And again, the x-intercepts, so the x-intercepts, you would have one at negative 4, 0, and then you'd have another one at 1, 0. So this is what we're working with. And just looking at the graph, this is f of x equals the quantity x plus 4 times the quantity x minus 1 times the quantity negative 2x squared minus 5x minus 9. So you'd have an x-intercept at negative 4, 0, and then another one at 1, 0. So just using that to split the number line up into intervals, you have anything that's less than negative 4, anything between negative 4 and 1, and then anything greater than 1. So you have your factor, which is x plus 4. So that's going to be negative here, and then positive here, and positive here. You have your factor x minus 1. That's negative here and here, and then positive here. And then your factor negative 2x squared minus 5x minus 9. Well, as we said before, that's negative here, here, and here. That's negative for all real numbers. So when we multiply these guys together, we have negative, 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 so that's a negative. Positive, negative, negative, so that's a positive. Positive, positive, negative, so that's a negative. So if we're looking for where this guy is less than or equal to 0, well, I'm looking at this right here and this right here. This is negative. Just make sure that you're including those critical values there. So you could say that x is less than or equal to negative 4, or x is greater than or equal to positive 1. So this is what we want. So we have an interval notation, again, coming from negative infinity, going up to and including negative 4, and then the union with anything that's greater than or equal to 1. So again, 1 would be included there. So graphically, this is filled in at -4, and then it's shaded to the left. This is filled in at 1 and then shaded to the right. If you want to use a bracket here or here, that would be fine. So again, coming back to the graph to check this, where are we 0? That's here and here. And then where are we less than 0? Where are we below the x-axis? That's going to be this piece of the graph right here, and then this piece of the graph right here. So that just confirms our answer, where again, we say that the x is less than or equal to -4, or x is greater than or equal to 1. All right, for problem 10, we have the quantity 3x squared plus x plus 2 times the quantity -2x squared minus x minus 1. This is less than or equal to 0. So again, if you see something like this, you have this quadratic here and this quadratic here, I would check them to see if you're going to get non-real complex zeros, and in each case you're going to. So this one up here, I've already pre-written everything. You would notice that your a value is going to be 3, and this is for this one. Your b value is going to be 1, and then your c value is going to be 2. So again, you're trying to do b squared minus 4ac and see if it's negative. Well, b is 1, so 1 squared minus 4 times a is 3, times c is 2. Well, if you go through and do the calculation, you're going to end up with -23. So this guy right here has 2 non-real complex zeros. Similarly, for this one, your a is going to be -2, your b is going to be -1, and your c is going to be -1 as well. So if you're doing b squared minus 4ac, well, b is -1, so -1 squared, minus 4 times your a is -2, times your c is -1. If you go through and do that, you're going to get -7. So again, this one's going to be 2 non-real complex zeros as well. I'm going to show you these both graphically. And so I put them on the same coordinate plane just so you can see. So this one up here is going to be f of x equals 3x squared plus x plus 2. So it's always going to be positive for all real numbers. And this one down here, g of x equals -2x squared minus x minus 1. It's always going to be negative for all real numbers. So neither one of these is going to have any x-intercepts. There's no point where it's going to cross over. So the reason this is an issue is if we consider, let me delete these. If we consider this problem, this for all real numbers is going to be positive. This for all real numbers is going to be negative. What do we know when we multiply a positive times a negative? Well, we get a negative. So that tells me that for this guy right here, it would always be negative, and a negative is always less than 0. So this would be true for all real numbers. This is true for all real numbers. That would be your solution here. And again, if you want to put this in interval notation, it's just from -infinity to +infinity, you would just shade the entire number line. And then graphically, if you want to look at this, this is your f of x equals the quantity 3x squared plus x plus 2 times the quantity -2x squared minus x minus 1. You can see that we're always, for all real numbers, going to be below the x-axis where the function values are negative. So that confirms our solution, where we're going to say all real numbers. All right, let's take a look at the practice test. For the instructions, we're asked to solve each variation problem. All right, let's take a look at the first problem. So the circumference of a circle varies directly with the radius. We are told that a circle with a radius of 10 inches has a circumference of approximately 62.83 inches. We want to find the approximate circumference of a circle when the radius is 12 inches. Now, what you'll see here is that I've written out the formula for finding the circumference of a circle from geometry. Now, we're not actually going to use this. I'm just putting this here for reference. When you have a direct variation problem, you want to say that y is equal to k times x. So k is known as the constant of variation. So that's not going to change. The idea is that once you figure that out, you can keep plugging in different values for x and you can figure out what y is. In this case, your k is 2 pi. So that's not going to change. What is going to change is the radius of the circle that we want to find the circumference for. In the first instance is 10 inches. Then it goes to 12 inches. But once you find out this 2 pi value here, your constant of variation, you can figure it out for anything. You can go 19 inches or 30 inches or whatever it is. So we're not going to use this formula. I'm just going to use something like this. So c for circumference is equal to k, and we're going to find that k is 2 pi, and it'll be an approximation because pi is an irrational number, and then times r, where r is the radius. So how do we figure this out? Again, you're going to plug in the initial values that you're given so you can figure out what k is. So that's what you do with a variation problem. So we get a circle with a radius of 10 inches, so we're plugging in 10 for r, has a circumference of approximately 62.83 inches. So you're plugging in a 62.83 for c. So that's where this is coming from and this is coming from. So all you have to do is divide both sides of the equation by 10. And what you're going to do is cancel this with this, and you're going to say that k, which is your constant variation, is equal to, it's going to be 62.83 divided by 10. So all you have to do is move this decimal point one place to the left because you're dividing by 10. So this would be 6.283. 3. Now that is not the exact value for 2 pi, again, because pi is an irrational number, but if you rounded 2 pi to the nearest thousandth, that's what you would get. Okay, so looking at this now, what you would do is you would take the known value for k and you would plug it in, and now you have something to where you can plug in whatever the radius is and you can get your circumference. So that's the goal of this type of problem. So you're going to say c for circumference is equal to the known value for k, that's 6.283. And then the radius, again, in this problem, we're told to find the circumference or the approximate circumference of a circle when the radius is 12 inches. So coming back, I'm just going to plug in a 12 right here. And so this would be equal to, let's say we get 75.396. Now, if you're asked to approximate this, and they don't give you a rounding place, what I would do is just go back to the problem. So you see this is 62.83, so this is rounded to the nearest hundredth. So you could just match that. So if you round this to the nearest hundredth, you would have 75.4. Some teachers will prefer that you use 2 decimal places here just to match what was given in the problem. So you can answer this by saying it's about 75.4 inches, or you can say 75.40 inches, again, just depending on your teacher. So let me just put inches there. All right, for problem 2. We are told that the distance a ball rolls down an inclined plane varies directly with the square of the time in seconds it spends rolling. So here's the initial information. After 2 seconds, the ball rolls 32 feet. Then we're asked, how far will the ball roll after 3 seconds? So again, you're trying to create a model, and then from that model, you're trying to figure out what is k, the constant of variation. Once you have that, you could just keep plugging in different scenarios and figuring out, well, how far is the ball going to roll after whatever amount of seconds you want to know. So initially, you would write your model. So d is your distance, and this is going to be in terms of feet, and t is your time, and this is going to be in seconds. So d is going to be equal to k, the constant of variation, times t squared. And again, the reason it's squared is because in the problem it says varies directly with the square of the time. Okay, so that's why it's squared. So once you have the model set up, all you do is plug in the initial information, you solve for k. That's all it is. So initially, we are told that after 2 seconds, so you're plugging in a 2 for t, the ball rolls 32 feet. So we come down here, you're plugging in a 32 for d. So this gets plugged in there, this gets plugged in there. So 2 squared times k is what's over here. We're going to divide both sides by 2 squared, or you can just put 4. And so what's going to happen is this is going to cancel with this, and then 32 over 4 is 8. So what you can say is that your k value, your constant of variation, is 8. And once you have that, you can just plug into the formula. So d is equal to, your k is 8, and then all you have to do is figure out what time you want to work with in seconds. You plug that in, and you'll have your distance in feet. So in the problem, it tells us how far will the ball roll after 3 seconds. So that means here, we want to go times, we'll have 3, and this would be squared like that. And I'm just going to say 3 squared is 9. 9 times 8 is 72. Let me show this. So 8 times 9, which equals 72. So this is in terms of feet. So when I give my answer, I'm just going to say it's going to be 72 feet. All right, for problem 3, we have at a local store, a cashier rang up a customer for a total of $196.02. The pre-tax amount was $180. How much will the next customer with $250 of merchandise pay after taxes? So even though it doesn't say it in the problem, this is a direct variation problem. Essentially, you can write y equals kx, where y is the total price after tax. K is going to be 1 plus the tax rate as a decimal, and then x is going to be the pre-tax price. In other words, what you're saying is that the total amount that you're spending after taxes is going to vary directly with the amount of merchandise that you're purchasing before taxes. The thing that's going to be constant here is the tax rate. And again, we need 1 plus the tax rate as a decimal to make this model work. So this right here, we're going to solve for that k. What we would do is we would plug in the initial amounts. So we're told, let me go back, that it's $196.02. That is the after-tax amount, and the pre-tax amount is $180. So coming back, 180 gets plugged in for x, 196.02 gets plugged in for y. So what you want to do is divide both sides of the equation by 180. And so this is going to cancel, and you're going to get that k is equal to 1.089. So essentially the tax rate there is 8.9%. Let me get rid of this. And now, again, you could just plug in. So you have a model to where you'll always know the after-tax amount. So y, that's the total price after tax, is equal to, you have 1 plus the tax rate as a decimal. So that's your k. Again, we found that's 1.089, and then times x. So in this case, your x, or the pre-tax amount, that's $250. So let's plug in a 250 there. And so this would be equal to, so I get 272.25. And just to answer this with the units, let's say it's going to be $272.25. That's going to be the price for that customer after tax. All right, for problem 4, we're told that under ideal conditions, the power obtained from a local windmill varies directly with the cube of the wind speed. So earlier today, when conditions were ideal, the windmill was producing 768 watts of power when the wind was blowing at 40 miles per hour. How much power in watts will the windmill produce under ideal conditions when the wind is blowing at 20 miles per hour? So the first thing you want to do again is just set up a model. This is direct variation as a power. So in other words, you could say y equals kx cubed, where y is the power that's being produced in watts, and x is the wind speed, again in miles per hour. Remember, you have to cube this because it says varies directly with the cube of the wind speed. Now I'm going to change the letters up. I'm going to use P for power, and I'm going to use S for wind speed. So P equals KS cubed. And then all you have to do is just plug in the initial information. So we're told that there's 768 watts of power being produced when the wind speed is 40 miles per hour. So 768 gets plugged in for P, 40 gets plugged in for S. Again, with this one, don't forget to cube it. Now, all you would do is solve for K, and you can divide both sides of the equation by 40 cubed. So for this one, again, if you're having trouble with your calculator, 40 cubed is 64,000. So you can just type in 768 divided by 64,000, or you can type in 768 divided by 40 cubed if your calculator will do it. This will cancel, and you're going to get K is equal to 0.012. So that's your value for K. So once we have that, we just update our model. So we'll say P, the power produced, again, this is going to be in watts, is equal to K. So that's going to be 0.012, and then times whatever S is, whatever that wind speed is, cubed. So let me go back up, and we're looking for how much power in watts will the windmill produce under ideal conditions when the wind is blowing at 20 miles per hour. So 20 is going to be for S, so we're going to plug that in there. Let me put a multiplication symbol in here just so I can separate this. So this is going to be times, you're going to have 20 here, and that is going to be cubed. Okay, so we're going to key this into the calculator, and I get exactly 96. So remember the units here, it's going to be in terms of watts. So I'm just going to answer that it's going to be 96 watts. All right, let's take a look at problem 5. So we're told that the speed of a pulley varies inversely with its diameter. At a local workshop, a pulley with a diameter of 4 inches has a speed of 112.5 revolutions per minute. Find the speed of a similar pulley with a diameter of 12 inches. So in this case, we have something that varies inversely. So the speed of a pulley varies inversely with its diameter. So let's use S for the speed of the pulley. Let's use D for the diameter. And this K here, again, that's your constant of variation. So this is just following our Y equals K over X like we talked about in the lesson. We're just using different letters. So in the initial situation, let me go back up. It's a pulley with a diameter of 4 inches. So the diameter, we're going to plug in a 4 for our D, and it has a speed of 112.5 revolutions per minute. So we're going to plug in 112.5 for the S. So coming down, again, you're plugging 112.5 in for S. You're plugging a 4 in for D. So you're using this to solve for K, the constant of variation. So all you have to do is multiply both sides of the equation by 4. So this would cancel. You're going to get K is equal to, in this case, 4 times 112.5 is 450. Again, once you have your value for K, let me just write it here more cleanly. So K equals 450. You could just plug it into the formula. So you could say that S is equal to 450 over D. Well, what we were asked for, if you come back, it says find the speed of a similar pulley with a diameter of 12 inches. So coming down here, you're going to put a 12 right here. And then you're just going to plug this into the calculator. So 450 divided by 12, that's going to be 37.5. This would be in terms of revolutions per minute. So let me write this out. I'm going to say 37.5 revolutions. Let me fix this U. And then per minute. All right, let's take a look at problem 6. So the amount of time it takes to go a given distance varies inversely with the rate of speed. On a field trip, a bus drives from New Orleans, Louisiana to Orlando, Florida for 13 hours at an average speed of 50 miles per hour. How long will the same trip take a teacher who averages 65 miles per hour? So this is just following the typical distance equals rate times time. But what we're doing here, we're saying that this is in terms of time, so it's going to vary inversely with the rate of speed. In other words, we're taking this distance formula, so distance equals rate times time, and we're solving it for t. So you divide both sides of the equation by r, this cancels, and you get this t, or time, is equal to distance over rate. So in this case, the distance is the constant of variation. Let me just delete this, because it's not going to change. The distance, provided that you go the same route, is going to be the same from New Orleans to Orlando. Again, I know that you could take different paths. You might stop for gas or something like that, but generally speaking, it's the same distance. So really, what's going to affect your time is the rate of speed. So how fast am I going in terms of miles per hour? So let's go back up. Initially, we're told that the bus travels for 13 hours at an average speed of 50 miles per hour. So coming back down, you're plugging in a 13 for the time, and you're plugging in a 50 for the rate. Now, if you solve for d, the distance, let me actually move this over here. I'm going to multiply both sides by 50 just to clear that denominator. So this would cancel, and you're going to get d, your distance, again, that's your constant variation here, is equal to 50 times 13. 5 times 13 is 65. And then just put a 0 at the end, so that's 650. So it tells me that the distance is 650 miles. So again, once I know that, I can figure out how long it's going to take me to get there because I can just play around with the rate of speed. If I come back, we're asked how long will the same trip take a teacher who averages 65 miles per hour? Well, all we're going to do is take that t is equal to, your distance here is 650 now. Let me move this up here, and it's over. Well, the rate is 65 miles per hour, so just plug in 65. And of course, we all know this is 10. You don't need a calculator for that. So the same trip is going to take that teacher 10 hours. So I'll just put here that it's going to take the teacher 10 hours. All right, for problem 7, we have that the electrical resistance of a wire varies directly with its length and inversely with the square of its diameter. So let me stop for a moment before we get into the information here. Let's think about the fact that we have a combined variation problem. So we have direct variation, and then we also have inverse variation as a power in this problem. So if you wanted to set up this model right here, which I've already done for us, what you would do is think about each part separately and then just merge the two. So let me do that off to the side here. So first, if we think about the direct variation part, so the electrical resistance of a wire, I'm going to call that R, varies directly with its length. So I'm going to call the length L. So let's go R is equal to K, that's your constant variation, and then times L. Now, I write my lowercase l like this. That might be easily confused with a 1, or maybe you think it's an I or something like that. So I'm just going to change it over into this right there, just so it's clear that I'm writing a lowercase l. So that would be your electrical resistance of a wire, R, varies directly with its length, L. Again, the K is the constant of variation there. Let me close this down with a border, and I'm going to put this for the inverse variation, and this is as a power because we have a square involved. So when we think about this, it says that the electrical resistance of a wire, let's write R again, is equal to what's varying inversely with the square of its diameter. So again, K, the constant of variation, is going to go in the numerator, and this would be over your diameter. Let's put that as a d, and of course the square of that, so it's d squared. So you're just going to merge these two together. Again, you're going to use R here for the electrical resistance of a wire, and that equals the K would be in the numerator, or you could put it out in front if you want. So you have a K here and a K here. And then you're only going to look at the fact that, well, L here would be in the numerator and D squared would be in the denominator. So that's how you're going to build this when you put them together. Again, this is telling me the electrical resistance of a wire varies directly with its length. So that's why this is up here, and inversely with the square of its diameter. That's why this is down here. Okay, let me get rid of this now that we understand where the model's coming from. If you get a question like this on a test or something, just stop and say, okay, what's the direct variation part? What's the inverse variation part? And then just merge the two together into one model. After you work a few problems, you won't need to do this. This will be pretty easy to set up. So for the information now, we have that a wire that is 4 meters long and 0.007 meters in diameter has a resistance of approximately 238 ohms. Find the approximate resistance in ohms of a wire made of the same material that is 5 meters long and 0.005 meters in diameter. All we have to do again is just plug in. You're going to plug in a 4 for the L, and you're going to plug in a 0.007 for the D there, and you're going to plug in a 238 for the R. So once you have that, you can solve for K. So I have that set up for us right here. Let me slide down here a little bit. So the fast way to solve for K, let's just multiply both sides by 0.007. This would be squared, and this would be over 4. Let me do that over here so it's legal. So we're going to multiply by 0.007 squared, and then this is over 4. Let me move this back in line right there. And of course, this would cancel with this, and then this would cancel with this. So we're going to put this as a 1 right there. So what you're going to get is that K is equal to, you can key this into the calculator. I get 0.0029155. If you're not getting that, try wrapping the numerator with parentheses and the denominator with parentheses. Again, it all depends on what calculator you have. If you're using an online calculator like Mathway or Symbolab, it'll take care of it without any issues. Okay, let's put this off to the side. We don't need this anymore. So now we have our value for K, and we can just update the model. So R is equal to, this is your K value. Let me just wrap this in parentheses. So 0.0029155. This is going to be multiplied by your L value. Let me go up. So for this one, it says find the approximate resistance in ohms of a wire made of the same material that is 5 meters long. So 5 is going to be for L. So let's put a 5 right there. And then this down here, we're going to get our diameter. And remember, we have to square that. So coming back, it says and 0.005 meters in diameter. So we want this 0.005 plugged in for D. So this down here is 0.005, and then we need to square that. Let's key this into the calculator, and I get 583.1. Again, this is going to be in terms of ohms. So I'm just going to write out the answer as 583.1 and then ohms. All right, for problem 8, we are told that the intensity of sound varies inversely with the square of the distance from the source of the sound. Jennifer is at a concert and decides to move to a seat that is double the distance from the loudspeakers. How would the intensity of the sound at her new seat compare to the intensity of the sound at her previous seat? So in this situation, we're not actually given a starting value where we have to plug in, solve for K, then plug something else in, and solve the problem. All we need to figure out is how would the intensity of the sound at her new seat, again, she's moving to a seat that's double the distance away from the loudspeakers, how does that compare to the intensity of the sound at her previous seat? So for this one, if you get this scenario, which is a very common question, what you would do is first just set up your model. So let me come down here. I have this ready for us. Let me just copy this, and I'll come back, and I'll just paste this in. So we're going to use L, a lowercase l for loudness. I'm not the best at writing L's. A lot of times I just write it like that and it looks like an I, so people get confused. So I'm just going to write it like this. So if you see that, that's going to be my lowercase l. So your L is equal to, again, if it's inverse variation, you have a K in the numerator and then your variables going in the denominator. So it says inversely with the square of the distance from the source of the sound. So we can use D for distance. And again, this is squared, so this is just D squared. So what you're going to end up doing, and this D looks like a 2. Let me fix that. So this is a D. Let me make that crystal clear. What you're going to end up doing is, because she's moving to a seat that's double the distance, you're going to replace this D with a 2D. So I'll come down here. I've already done that. So replace the D with a 2D because it's twice the distance. And then all you have to do is simplify. So let me do that up here. So if we have L, again, that's my lowercase l, is equal to K over, you would have 2D squared. Remember how this rule applies. This exponent of 2 is applied to the 2 and then the D, because this is multiplication inside here. So it goes to each factor. So this is K over 2 squared times D squared, which would be equal to K over 4D squared. Now let me erase this scratch work, and let me say this L is equal to, you're going to have your K over 4D squared. Now, if you think about it, you could really write this, let me erase it once again, as 1/4, you could put that out in front, times this K over D squared. So this right here is a scale factor. In other words, when you think about it, it's 1/4 in terms of the intensity of the sound at her new seat compared to the intensity of the sound at her old seat. So it's going to be a quarter or 1/4 of what it was. So you could put the answer as a fraction. So you could write it's 1/4 of what it was. You could also put 0.25, or you could even say it's 25% if you want to answer it that way. All of these are common answers. All right, for problem 9, we have the apparent brightness of a car headlight varies directly with the luminosity, so that's measured in watts, and varies inversely with the square of the distance, so that's measured in meters, from the headlight. If the luminosity was quadrupled, so that means multiplied by 4, and the distance from the headlight was 1/3 of its original, by what factor will the brightness change? So for this one, what you would do is just start off with your model. So let me grab this and I'll go back up. Let me paste this in, put this right there, slide down a little bit. So you have combined variation. So you have direct variation and inverse variation together. And again, when you think about it, the apparent brightness, so we're using lowercase b for that, of a car headlight varies directly with the luminosity. So this L right here, again, when I write this out, I'm going to use a lowercase l like that so we're not confused with I. So that's the luminosity here. That's what it varies directly with. And it varies inversely with the square of the distance. So that's why you have d squared down here. And of course, you have your k in the numerator as your constant variation. Some people will write this as b is equal to, you might put your k like this, and then times your L over d squared. You can do it that way, or you can just put it in the numerator. It's really up to you. Again, all you're going to do is plug in, and then you're going to compare it to the original model. We want to know if the luminosity, so that L right there, was quadrupled. So if it was multiplied by 4. So in other words, if you had 4L. So coming down here, that's why we have 4L and then times your K. And we would also say that the distance from the headlight was 1/3 of its original. So the D, the distance, you're going to change that to 1/3 of D. And so that's going to be squared. So come down here, you have 1/3 D, and that's going to be squared. Okay, so let me put a little border here, and we're just going to simplify this. So B is equal to, you have your 4. Let me write this separately. So you're going to have 1/3 squared times D squared. So let me put, so this is crystal clear, 4 over 1 over, this would be 1/3 squared. We know that would be 1/9, so let me just write that now. So times, so I'm going to write, you would just have this part right here. Again, I already took the 4 and wrote it as 4 over 1. So you're going to have your L, K, over, down here you would just have D squared. So hopefully that does make sense. The reason I'm splitting this up is because this right here is going to match this right here. What we want to know is, what is this right here? So we know by what factor has the apparent brightness changed. So this right here is 4 over 1 divided by 1/9. So that's equal to 4 over 1 times 9 over 1. And then times, you have your L, K over D squared. And so 4 times 9 would be 36. So this would really be, let me erase everything, 36. So times this right here. So your L, K over D squared. So when they ask, by what factor will the brightness change? Well, it's going to be 36. So it's going to be this right here. So just to write the answer, it would be 36. All right, let's take a look at problem 10. So here we're told that the owners of a local gym find that the sales of memberships each month vary directly with their advertising budget and inversely with the monthly membership fee. So if 2,000 new members are added when the advertising budget is $50,000 and the price of their monthly membership is $50, how many new members are added when the advertising budget is $75,000 and the price of their monthly membership is $60? Okay, this one's fairly straightforward. So it is combined variation, but again, we're back to the plug and chug thing. So let's go down, and I set up a little model. Again, if you want to use different letters, that's up to you. But essentially, we know that Y is the monthly membership sales. So that's what we're interested in. And it varies directly with the advertising budget. So in other words, they spend more on their advertising budget, they get more people to buy monthly memberships. That should make sense because as you spend more on advertising, more people see it and then more people buy it. So Y equals, this is the KX part. But it varies inversely with the price of a monthly membership. So that's Z that's going down the denominator. And that should also make sense because as the price of the monthly membership goes up, fewer people are going to want to buy a monthly membership. So we have Y equals KX over Z. So then again, you're just going to plug in to find out what K is. And initially we're told you have 2,000 new members that are going to be added when the advertising budget is $50,000 and the price of their monthly membership is $50. So that means that the monthly membership sales, the Y is 2,000. The X, the advertising budget, that's 50,000. So that's going in for your X. Again, I'm putting the K out there. And 50 that's going in for Z, that's the price of the monthly membership. So essentially what you would do here, let me just move this like this. I'm going to multiply both sides by 50. Let me put a little border here. And then this is going to cancel with this. 50 times 2,000, 5 times 2 is 10. And you have 1, 2, 3, 4 trailing zeros. 1, 2, 3, 4 trailing zeros. So let me come through here and put a comma in there. So that means it's going to be 100,000 is equal to, this would be 50,000 K. And then what we're going to do is divide both sides of the equation by 50,000. And of course, most of us know this is going to be 2. Let's just go through it. So this is going to cancel with this. And we could say that K is equal to 100,000 over 50,000, which is 2. So let me erase everything. And we can leave that right there. I'll just put a border back in. I'm just going to say that K is equal to 2. So then you just rewrite this. Let me put another border. So y is equal to, k is 2, then times, what is x? Let's go back up. We're trying to figure out, well, when the advertising budget is $75,000, so $75,000 is your x, and the price of the monthly membership is $60, so z is 60. This is going to be 2 times 75,000 over 60. I think it would make it easier on your calculator to just cancel this with this and put 30 down here. And then you could just punch in 75,000 over 30 in your calculator. And let me fix this 3. And that's going to give me 2,500. So basically, you're going to end up with 2,500 or 2,500 new members.